For decades, the far side of the moon has been a realm of mystery, shrouded in shadows and secrets. Unlike the familiar cratered landscape we see from our planet, this dark side has remained largely unexplored, whispering hints of stories billions of years in the making. But now NASA's latest missions have pierced that veil of darkness, uncovering astonishing surprises that challenge everything we thought we knew about our closest celestial neighbour. From hidden water ice to strange mineral deposits and baffling geological formations, the moon's hidden face is revealing a world as alien as it is fascinating. What mysteries await on the moon's hidden far side, and why does NASA remain so captivated by it? Before we begin, tell us where you're tuning in from and what time it is for you right now in the comments below. Now, settle in for a journey to the darkest side of the moon that will change the way you see it forever. The moon has always presented the same familiar face to those of us on Earth. For as long as human eyes have wandered skyward, we have seen its patchwork of dark, smooth volcanic plains, known as Maria, and the bright, rugged highlands marked with countless craters. This enduring familiarity is not a mere illusion of distance or lighting. It is a fundamental trait of the moon itself, a cosmic behaviour known as tidal locking. Grasping the nature of tidal locking is essential for understanding why one side of the moon remained hidden from human sight for countless millennia, wrapped in mystery until the advent of modern space exploration. Tidal locking occurs when the gravitational pull of a larger celestial body, in this case, Earth, gradually influences the rotation of a smaller orbiting body, like the moon. Over unimaginably long stretches of cosmic time, Earth's gravity exerted a subtle but relentless tug on the moon. The moon is not a perfect sphere. It has tiny bulges on the side facing Earth and the opposite side. These bulges form because Earth's gravity pulls slightly more on the near side than the far side, stretching the moon along the imaginary line connecting the two worlds. This uneven pull creates what scientists call a tidal bulge. Picture the early moon spinning far faster than it does today. As it circled Earth, the planet's gravity constantly tried to pull its bulges back into alignment, much like how Earth's gravity tugs on its oceans, producing tides. This ceaseless gravitational pull acted like a brake, gradually slowing the moon's rotation. Over hundreds of millions and perhaps even billions of years, this braking process continued. The moon's rotational energy slowly dissipated, mostly through internal friction within its rocky interior, which produced tiny amounts of heat. This process was relentless, steady, and irreversible until the moon reached a state of equilibrium. Equilibrium occurs when the moon's rotation period, the time it takes to spin once on its axis, matches exactly its orbital period, the time it takes to circle Earth. In simpler terms, the moon spins once in the same time it takes to complete one orbit around our planet. This perfect synchronization means that the same hemisphere always faces Earth. From our vantage point, it seems as though the moon is not spinning at all. In reality, it is spinning, but its rotation is perfectly matched to its orbit. Imagine a person walking around a merry-go-round while always facing its center. Relative to the outside world, they rotate, but relative to the central pole of the merry-go-round, they appear stationary. For the moon, this alignment minimizes Earth's gravitational stress, locking it in the stable, tidally locked orientation we observe today. This is not an unusual situation. Many moons across our solar system are tidally locked to their parent planets. Take Charon, the largest moon of the dwarf planet Pluto. Charon is tidally locked to Pluto, and Pluto is tidally locked to Charon. They always present the same faces to one another. Such outcomes are common when smaller bodies orbit close to massive ones over vast stretches of time. The underlying physics involves the transfer of angular momentum and the pursuit of the most energy-efficient configuration in a gravitational system. Although we generally see the same side of the moon, over time, slightly more than 50% of its surface comes into view. This effect is due to a phenomenon called libration, a subtle wobbling or oscillation in the moon's apparent position as seen from Earth. Several types of librations exist. Optical librations, for instance, result from the shape of the moon's orbit around Earth. The moon travels in an elliptical path, not a perfect circle. When it is closer to Earth, it moves a bit faster, and when it is farther away, it moves slightly slower, yet its rotation speed remains nearly constant. This mismatch allows us occasional glimpses around its eastern and western edges, revealing a little more of its hidden terrain. Another type of libration comes from the tilt of the Moon's axis relative to its orbit. Just as Earth's tilt creates the seasons, the Moon's tilt lets us peek slightly over its north and south poles at different times. The result is that, although 50% of the Moon is always visible, and another 50% is always hidden, an extra sliver of about 9% along the edges can swing into view at certain times. Over the course of a full lunar cycle, this allows us to observe roughly 59% of the Moon's total surface, yet the remaining 41%, the far side, remains permanently invisible from Earth, a vast hidden realm that for ages stoked human curiosity. Because the far side could not be seen from Earth, its features, landscapes, and true nature remained entirely speculative for thousands of years. Ancient astronomers could map the near side in increasing detail, even giving names to craters and seas, but the opposite hemisphere was a blank canvas. No telescope, no matter how sophisticated, could bend light around the Moon to reveal the unseen half. From Galileo Galilei's rudimentary spyglass in the 17th century to the enormous observatories of the 20th century, instruments were constrained by the Moon's tidally locked orientation. Humanity could only study what was presented. The far side steadfastly concealed itself. Early lunar maps were therefore necessarily incomplete. They showed only the visible hemisphere, leaving the far side to imagination, artistic rendering, and educated guesswork. Without direct observation, scientists could only speculate, some assuming the far side mirrored the near side, others envisioning an entirely different landscape. The invention of photography in the 19th century allowed detailed and permanent records of the near side, but it offered no insight into the hidden hemisphere. As mapping techniques improved, producing ever more intricate charts, the far side remained a mysterious void. The mystery endured because humanity lacked a crucial technological breakthrough: space travel. Until the mid-20th century, sending probes beyond Earth's atmosphere was mostly a dream confined to the pages of science fiction. The challenges were enormous: rockets powerful enough to escape Earth's gravity, guidance systems capable of precise navigation across millions of kilometers, and communication systems able to send data back from interplanetary space. These were formidable obstacles, pushing the limits of contemporary engineering and scientific understanding. The space age, ignited by the Soviet Union's launch of Sputnik 1 in the mid-1950s, changed everything. Suddenly, the impossible became achievable. The race to the Moon accelerated, driven by both geopolitical rivalry and insatiable scientific curiosity. Yet even with powerful rockets, observing the far side posed a new and immediate challenge: communication. A spacecraft on the far side would be completely blocked by the Moon itself, with no direct line of sight to Earth. Imagine trying to shout to someone on the opposite side of a huge hill. Your voice cannot travel. Similarly, any data or images collected by a far-side probe would be trapped unless a solution was devised. This led to the development of relay technologies, satellites in orbit that could catch signals from a far-side probe and transmit them back to Earth. Without such systems, long-term missions to the Moon's hidden hemisphere would have been impossible. The first successful glimpse of the far side came from the Soviet Union. In October of 1959, the Lunar 3 spacecraft circled the Moon, becoming the first probe to photograph this mysterious territory. The images were crude and blurry by today's standards, distorted by early camera technology and vast distances, but they were revolutionary. They revealed a landscape far more heavily cratered than the near side, with almost no dark volcanic plains or maria. The far side was not a mirror image. It had its own distinct geological character, hinting at a separate evolutionary history. These first images sparked immense excitement, opening the door to entirely new scientific discoveries and forever changing humanity's understanding of its closest cosmic companion. The first images captured by Lunar 3 were tantalizing glimpses, a tiny peek behind the Moon's shadowed veil. Yet, they were only the beginning, far from giving a complete understanding of the Moon's mysterious far side. At that time, NASA was still a young space agency, full of ambition and curiosity, determined to explore our nearest celestial neighbour, it launched a series of missions that would lay the foundations for decades of lunar research. The Surveyor program sent uncrewed landers to gently touch down on the surface, while the Lunar Orbiter missions took high-resolution photographs, mapping the familiar near side of the Moon in preparation for human landings. These early missions focused mostly on the side visible from Earth, primarily because it was easier to land there and maintain communication. Yet scientists everywhere remained fascinated by the far side, the part that had remained hidden for millennia. Exploring the Moon required more than just powerful rockets. It demanded careful planning, inventive engineering, and years of international collaboration, and sometimes competition. The drive to uncover the unseen was not mere curiosity. It was about answering deep questions regarding the Moon's history. Was the far side older than the near side? Had it suffered a different pattern of asteroid impacts? Did it contain unique materials or geological structures that could reveal secrets about the early solar system? These questions became the fuel for exploration, shaping both scientific objectives and mission designs. NASA's approach was step by step, gradually increasing in sophistication. First came flyby missions like Luna 3, offering brief, fleeting images. Next were orbiters, which could circle the Moon and map its entire surface in detail, gathering consistent data over extended periods. The ultimate challenge was landing softly on the surface, collecting samples, and analysing them directly. Each stage built upon the previous one, improving navigation, imaging, and communication methods. Advances in miniaturized electronics, stronger antennas, and more reliable power systems were crucial. For missions targeting the far side, the challenge of communicating with Earth became especially pressing. Without a relay system to bounce signals, spacecraft could find themselves completely isolated from mission control. The importance of communication satellites, or relay satellites, cannot be overstated. Any long-term operation on the Moon's far side, whether robotic or human, depends on a network of orbiting satellites. These satellites act as middlemen, receiving data from surface equipment and sending commands back from Earth, effectively bridging the Moon's hidden side with our planet. This solution overcame a fundamental problem. The far side of the Moon can never see Earth directly, which is why it remained a mystery for so long. Exploring the far side is a testament to human persistence and ingenuity. From centuries of total ignorance, to the blurry first images, to the precise topographical maps and geological surveys of today, our knowledge has grown immensely. The far side is no longer a blank, shadowy expanse. It is a landscape filled with clues about the Moon's dramatic past, its unique geological features, and even its potential as a site for future observatories protected from Earth's radio interference. The journey to uncover its secrets has been long and challenging, but it is steadily paying off, driven by humanity's enduring desire to explore the unknown. It is remarkable to think how far we have come, from staring at a single, unchanging face in the night sky, to actively mapping and studying the Moon in its entirety. From the very beginning, scientists were intrigued by the stark differences between the Moon's two hemispheres. The near side is dominated by vast dark plains called Maria, created by ancient volcanic eruptions. These areas are relatively smooth and lightly cratered. The far side, by contrast, is rugged and heavily cratered, with only a few Maria. This dramatic contrast provides vital clues about the Moon's history. Scientists theorize that the near side has a thinner crust, which allowed molten lava to break through and form the Maria. The far side, with its thicker crust, resisted such volcanic activity. Discovering this difference in crust thickness and composition was one of the far side's most important revelations. Subsequent NASA missions refined these theories by measuring crustal thickness and mapping the Moon's elemental composition across both hemispheres. Comparing the near and far sides has revealed insights into the Moon's interior and how it responded to early solar system events. In many ways, the far side is a geological Rosetta Stone, holding answers to questions about the Moon's formation and early evolution. This story of discovery relied on remarkable technological progress. Rocket engines became more powerful, capable of lifting heavier spacecraft into space. Navigation systems evolved from simple star sightings to complex inertial guidance, and eventually lunar GPS-like networks for orbiters. Communication technology advanced from basic radio waves to high-speed links capable of sending images and scientific data across millions of kilometers. Power systems moved from short-lived batteries to solar panels and radioisotope generators. Scientific instruments grew increasingly precise. Cameras were joined by spectrometers that identified minerals, altimeters that measured terrain with incredible accuracy, and gravimeters that detected subtle variations in the Moon's gravitational field. All of these tools allowed missions to peel back layer after layer of the far side's mysteries. For future missions, communication remains a critical concern. Any human or robotic outpost on the far side will require a network of relay satellites, carefully placed to maintain constant contact with both Earth and the surface base. Without these satellites, operations would be limited to short windows when the Moon's rotation occasionally exposed the base, or would demand extreme power to send signals around the Moon, a near impossible task. The relay system is as essential as the landers themselves, forming the invisible bridge that makes long-term exploration of the hidden hemisphere possible. The far side's importance goes beyond geology. Shielded from Earth's radio noise, it offers a unique environment for radio astronomy. Observatories there could detect faint signals from the early universe, signals that are currently drowned out by human-made interference on Earth. This makes the far side a highly coveted location for scientific research. Long-term lunar exploration may one day include human habitats and understanding the far side's conditions. Radiation, temperature extremes, and surface properties is crucial to their safety and sustainability. Every piece of data gathered by NASA missions brings this vision closer to reality, turning the once-hidden Moon into a frontier for humanity's expansion. Studying the far side not only illuminates the Moon itself, but also deepens our understanding of the cosmos, revealing the subtle interplay of gravity and the slow, relentless passage of geological time. The hidden Moon stands as a monument to human curiosity, perseverance, and technological ingenuity, continually revealing wonders that were once beyond imagination. Human fascination with the Moon and with the stars beyond has stretched back to the very dawn of our existence. Long before the rise of scientific inquiry, before the invention of telescopes, and long before humans even dreamed of leaving Earth, the Moon was a magical and mysterious presence in the night sky. Its silvery glow inspired awe, wonder, and countless stories. Ancient civilizations across every continent looked up and wove elaborate myths around this glowing orb. They saw it as a powerful deity, a divine chariot rolling across the heavens, a watchful eye, or a force controlling the tides and marking the passage of time. The Moon was less an object to study and more a symbol of the mystical, the spiritual, and the unknown. Yet even in those distant times, curious minds began to imagine something more tangible. Philosophers like Anaxagoras, a Greek thinker of the 5th century before the Common Era, boldly proposed that the Moon was not a divine light, but a solid, rocky world, reflecting the sun's illumination much like the Earth does. This idea was revolutionary, shaking the mystical worldview of the era and planting the earliest seeds of scientific thinking. Aristotle, another great Greek philosopher, would later take these ideas further, weaving them into his geocentric vision of the universe, where Earth sat immobile at the centre, and the stars and planets traced perfect circular paths around it. While his model would eventually be proven incorrect, Aristotle's systematic method of observing and theorizing about the cosmos guided thinkers for more than 1,000 years. Slowly, the notion of the Moon as a real physical world began to take root. Alongside these philosophical musings, the human dream of flight stirred imaginations. The ancient myth of Icarus, who dared to soar toward the sun on wings of wax, symbolized an enduring yearning, the desire to rise above the earth and touch the skies. Though these were not dreams of space travel in the modern sense, they revealed a deep, universal longing to leave the ground behind, a prelude to the far grander ambition of reaching other worlds. For centuries, however, the laws of physics and the principles of gravity and air pressure remained mysteries, and journeys to the Moon belonged purely to the realm of myth, poetry, and storytelling. Engineers and scientists had little to work with. The Moon was a stage for imagination, not machinery. Everything began to change in the 17th century, as the scientific revolution began to illuminate the universe in a new light. The invention of the telescope by Hans Lippershey, followed by its masterful application by Galileo Galilei in the early 1600s, transformed humanity's understanding of the moon. Galileo's observations revealed a rugged landscape of mountains, valleys, and craters, proving that the moon was no smooth, ethereal sphere, but a world in its own right. He even measured the heights of lunar mountains by observing the shadows they cast, a remarkable leap toward understanding another celestial body through evidence rather than myth. The moon had become real, tangible, and intriguing, inspiring imaginations to leap from mystical reverie to the beginnings of imaginative exploration. Fueled by this new scientific insight, writers began envisioning how humans might one day reach the moon. In the mid-1600s, the French playwright and duelist Cyrano de Bergerac penned The Other World, comical history of the states and empires of the moon, imagining journeys lifted by bottles of evaporating dew or rockets fueled by firecrackers. Around the same time, English Bishop Francis Godwin published The Man in the Moon, telling the tale of a protagonist journeying to the moon in a contraption pulled by trained geese. While purely fantastical, these works were extraordinary in that they imagined not just reaching the moon, but life and society upon it. They speculated on challenges like gravity and the need for air, planting the seeds for future scientific thought about space travel. By the 18th and 19th centuries, this blend of imagination and scientific curiosity blossomed further. The French novelist Jules Verne, writing in the 19th century, became a titan of early science fiction. His novel, From the Earth to the Moon, written in 1865, imagined launching humans to the moon in a giant cannon. Though impossible in reality, given the deadly forces involved, Verne meticulously calculated trajectories, velocities, and dimensions, demonstrating an extraordinary effort to root his story in the science of his day. He described the experience of weightlessness and the difficulties of living inside a flying projectile, thrilling readers while introducing them to the principles of ballistics. Meanwhile, English author H.G. Wells, in his 1901 novel The First Men in the Moon, took a different approach, imagining a material called cavarit that could neutralize gravity and allow controlled lunar travel. Wells also populated the moon with an alien civilization, blending scientific curiosity with sociological and philosophical speculation. Together, these literary works sparked a widespread fascination with space, bridging the gap between pure fantasy and scientific possibility. They inspired generations to look beyond Earth, turning the moon from a distant mystical light in the sky into a destination that might one day be reached by human hands. The real seeds of space travel were planted long before humans ever left the ground, sown by a handful of extraordinary visionaries in the late 19th and early 20th centuries. These thinkers often worked alone, far from the spotlight, facing skepticism from colleagues and the public alike. Among them, the Russian schoolteacher and self-taught scientist Konstantin Tsiolkovsky shines as one of the earliest and most profound pioneers of astronautics. Living in relative isolation during the final decades of the 1800s and the early years of the 1900s, Tsiolkovsky began to uncover the fundamental principles of rocketry. He famously devised what became known as the rocket equation, a mathematical formula that calculated how fast a rocket could travel, depending on the speed of its exhaust and the ratio of the rocket's initial mass to its mass after burning fuel. This simple yet powerful equation revealed a startling truth. Achieving spaceflight required rockets with high exhaust speeds and extremely efficient use of fuel. Tsiolkovsky also championed liquid-fueled rockets, recognizing that they could produce far greater thrust and be controlled more precisely than solid-fueled alternatives. He imagined multi-stage rockets, understanding that discarding spent fuel tanks and engines mid-flight could drastically improve efficiency and allow rockets to reach higher speeds. He even envisioned using liquid oxygen and liquid hydrogen as rocket fuels, choices that remain central to modern spaceflight due to their incredible energy potential. Beyond calculations and fuels, Tsiolkovsky was a dreamer and philosopher. He saw humanity's future not just on Earth, but among the stars, imagining space stations, lunar bases, and even the colonization of the solar system. While much of his work was little known outside Russia during his lifetime, it laid the theoretical groundwork for generations of rocket engineers to come. Meanwhile, across the Atlantic, the American physicist Robert Goddard was pursuing his own revolutionary ideas, Ridiculed by newspapers and misunderstood by the public for daring to dream of space, Goddard quietly conducted meticulous experiments. In 1926, he achieved a landmark success, the launch of the world's first liquid-fueled rocket, nicknamed Bell. Though it travelled only a short distance for a few fleeting seconds, this small flight proved that liquid propellant rockets could work in practice, not just in theory. Goddard spent the rest of his career refining rockets, often working with limited funds and resources, patenting innovations such as multi-stage designs, fuel pumps, and guidance systems. His careful, hands-on approach bridged the gap between Tsiolkovsky's equations and the practical engineering needed to turn theory into reality. In Germany, another towering figure, physicist and engineer Hermann Oberth, was also shaping the future of space travel. His book, The Rocket into Interplanetary Space, published in 1923, explored the physics and mathematics of rocket propulsion in great detail. Oberth contributed ideas about space stations and the use of rockets for scientific exploration, inspiring a generation of German engineers, including Wernher von Braun, who would later play a decisive role in both military rocketry and the American space program. Together, Tsiolkovsky, Goddard, and Oberth are remembered as the fathers of rocketry. Though working independently, their ideas converged to form the foundation of modern astronautics. They showed that escape velocity, the speed needed to break free from a planet's gravity, was not just a dream, but an attainable goal. They also applied Newton's centuries-old principle of action and reaction to rockets, proving that by expelling mass backward, a rocket could propel itself forward into the vastness of space. The brutal reality of World War II, as tragic as it was, accelerated rocketry in ways the pioneers could scarcely have imagined. Under the leadership of Wernher von Braun, Germany developed the V2 rocket, the first large-scale liquid-fueled missile capable of reaching the edge of space. Though designed as a weapon of war, the V2 demonstrated the extraordinary power and potential of rocket technology. After the war, both the United States and the Soviet Union brought German engineers and V2 technology into their own programs, gaining a crucial head start in missile development and eventually space exploration. By the mid-20th century, the Cold War added a powerful new driver for space travel. The fierce rivalry between the United States and the Soviet Union transformed space into a stage for demonstrating technological and ideological superiority. When the Soviet Union launched Sputnik 1 in October of 1957, the very first artificial satellite to orbit Earth, it sent shockwaves across America. The launch revealed Soviet technical prowess and sparked an urgent determination in the United States to catch up and then surpass their rivals. This urgency led directly to the creation of the National Aeronautics and Space Administration, or NASA, in 1958, uniting various American space efforts under a single agency. The initial mission was clear: close the gap with the Soviets and ultimately send a human to the moon. Before NASA, many smaller organizations had worked on aerospace research, but Sputnik made it obvious that a coordinated national effort was essential. Public imagination, already fueled by decades of science fiction, now fully embraced the idea of space travel. The moon, once the realm of dreams and stories, became a tangible goal, supported by massive government funding and political will. The space race transformed early, isolated scientific ideas into a massive, coordinated endeavour involving hundreds of thousands of engineers, scientists, and technicians. The leap from dreams to missions was powered by curiosity, ingenuity, and competition, turning humanity's long-held visions of the stars into a reality. Out of this extraordinary period emerged the very concepts of astronaut and cosmonaut, forever altering our understanding of our place in the universe. For countless thousands of years, the far side of the moon remained one of the greatest mysteries in the sky. From our vantage point on Earth, we have always seen only one face of this familiar celestial companion, a result of what scientists call tidal locking. This phenomenon causes the moon to rotate in perfect synchrony with its orbit around Earth, ensuring that the same side is always turned toward us. The hidden hemisphere, forever cloaked from human eyes, could only be revealed through a monumental leap in technology, machines capable of leaving Earth's gravity, navigating through the void of space, and circling the moon itself. The mid-20th century marked the dawn of this new age of exploration. At the time, a fierce rivalry known as the space race was underway between the Soviet Union and the United States. Both nations poured immense resources into developing rockets, satellites, and spacecraft, each striving to achieve milestones in space before the other. It was the Soviet Union, benefiting from early advancements in rocketry, that became the first to pierce the veil of the moon's far side, providing humanity with its first, blurry but profoundly important glimpses of the terrain that had never been seen. This historic achievement was accomplished by the robotic probe known as Luna 3, launched by the Soviet Union in the month of October, in the year 1959. This launch came just over 2 years after the astonishing debut of Sputnik 1, Earth's first artificial satellite, which had stunned the world and set the stage for the intense competition that followed. Luna 3's mission was daring and ambitious. It was to travel not merely around Earth, but onward toward the moon, swing around the unseen side, and transmit images back across the vast emptiness of space. Its goal was simple in words but revolutionary in impact: to capture photographs of the moon's hidden face, a landscape never before observed by human eyes or any instrument built on Earth. The spacecraft itself was a marvel of engineering for the late 1950s, designed within the constraints of the technology available at the time. Shaped like a cylinder that tapered at one end, Luna 3 was equipped with solar panels for power, antennas for communication, and a specially designed imaging system. The cameras it carried were primitive compared to modern standards, yet revolutionary for their era, consisting of 2 lenses with different focal lengths to capture both wide-angle vistas and closer, more detailed shots. Perhaps the most remarkable feature of this system was its onboard ability to develop the film. Using traditional photographic film, the spacecraft could automatically develop, fix and dry the images while hurtling through the harsh vacuum of space, a feat that combined ingenuity with technical daring. Once the film was developed, the images had to be converted into a form that could travel the hundreds of thousands of miles back to Earth. This was achieved using a technique similar to early television broadcasting. A tiny beam of light scanned the film line by line, reading variations in brightness and shadow. These variations were then translated into an electrical signal, which was transmitted via radio waves to Earth. The process was prone to interference, resulting in images that were often blurry and streaked, but it represented the cutting edge of remote imaging and long-distance communication for its time. Receiving these faint signals on Earth required enormous antennas and sophisticated equipment to reconstruct even the simplest details of the lunar surface. The trajectory of Luna 3 was itself a triumph of early space navigation. Rather than entering orbit or landing on the moon, the spacecraft was designed for a circumlunar flyby. It launched from Earth, travelled directly toward the moon, and then used the moon's gravity to swing around its far side before returning to Earth. This clever use of gravitational assist allowed the spacecraft to follow the correct path without carrying excessive fuel. Timing was critical. Photographs could only be taken when the far side was illuminated by the sun and when the spacecraft was positioned at the correct angle to capture the images. On the 7th day of October, in the year 1959, Luna 3 arced around the moon, and its cameras began capturing the first ever images of the hidden hemisphere. When transmitted back to Earth, the images were far from perfect. They were blurry, low in resolution, and often marred by streaks or static caused by the long-distance transmission. Yet, despite these flaws, they were breathtaking. For the first time, humanity glimpsed what lay on the moon's mysterious far side. The initial photographs revealed a dramatic contrast between the familiar near side and the hidden far side. The near side, visible from Earth, is characterized by large dark plains called maria, formed from ancient volcanic lava flows that later solidified into smooth basins. These maria cover vast stretches of the surface, giving the moon its familiar face-like appearance. The far side, in contrast, was almost entirely rugged and cratered, lacking the expansive dark plains. Only a few small irregular patches of darker terrain appeared, such as what would later be named Mare Moscoviense, or Moscow Sea, and Mare Smithy, a smaller area that extends partially onto the near side. This rugged, heavily cratered landscape suggested that the far side had undergone a different geological history from the near side, The abundance of craters implied an older, more stable surface, largely untouched by the lava flows that reshaped the near side. These early images hinted at fundamental differences in the Moon's crust and internal structure between the two hemispheres, challenging assumptions that the Moon was uniform in its composition and development. Scientists quickly speculated that the thicker crust on the far side made it more difficult for magma to reach the surface, explaining the absence of large maria. This hypothesis would later be confirmed by subsequent missions. The images also offered further evidence of the intense bombardment that the early solar system experienced, with the far side preserving a more complete record of these ancient impacts. The discovery also began a process of naming features on this previously unknown terrain. The most prominent cratered basin captured by Luna 3 was named Tsiolkovsky, in honor of Konstantin Tsiolkovsky, the Russian rocket scientist whose pioneering work had laid the foundation for space travel. Other features received names celebrating Soviet achievements in exploration, beginning the first maps of a lunar hemisphere that had, until then, been entirely hidden from human eyes. The achievement of Luna 3 sent ripples far beyond the narrow corridors of scientific research. For the Soviet Union, it was more than a scientific milestone. It was a dazzling victory in the fierce competition of the space race, a striking demonstration that their technological prowess was still ahead of the world. To the general public, it was nothing short of breathtaking. Suddenly the Moon, which had long seemed distant, cold and enigmatic, felt more tangible, almost like a real place waiting to be explored, though still strange and alien. The grainy, pioneering photographs captured by Luna 3 ignited imaginations everywhere, sparking public fascination and fueling the curiosity of scientists eager to uncover the Moon's secrets. These images confirmed, in a powerful way, that humanity had taken its first steps beyond the confines of Earth, capable of reaching out to other celestial bodies and glimpsing the unknown. The data gathered by Luna 3 proved invaluable for planning future missions, influencing both Soviet and American space programs. For the United States, which at the time was just beginning to establish the National Aeronautics and Space Administration and plan its own lunar explorations, the findings were like a treasure trove of intelligence. The images highlighted the importance of mapping and studying the Moon's far side, not just the familiar face that had gazed down on Earth for countless millennia. Luna 3's success in navigating orbit, capturing remote images, and transmitting signals across vast stretches of space, though a Soviet triumph, offered lessons that could be analysed and adapted by any nation daring to venture beyond the Earth. Beyond its immediate political and practical impact, Luna 3 offered profound scientific insights. Its images provided a first clear view of tidal locking in action. By revealing the stark contrast between the Moon's near side and its far side, they illustrated how Earth's gravitational pull had not only frozen the Moon's rotation, but had also shaped its geology in markedly uneven ways. The far side was not merely the other side. It was a completely different world, moulded over billions of years by cosmic forces. These first blurry photographs became more than just images. They were windows into a hidden lunar landscape, inviting new questions, fresh exploration, and a shift from speculation to observation. Humanity was beginning to see the Moon as it truly was. The importance of these first images cannot be overstated. Before Luna 3, the far side of the Moon was almost entirely the domain of guesswork. Some scientists imagined it might resemble the familiar near side, smooth and patterned with dark plains and bright highlands. Others speculated that it might be dramatically different, but without photographs, such ideas were mere conjecture. Luna 3 provided the first solid proof that the Moon was asymmetrical, a revelation that sparked intense scientific debate and research. New theories about the Moon's formation and evolution took shape. One influential idea, strengthened by these images, suggested that the far side's crust was much thicker than the near side's, preventing widespread volcanic activity and the formation of large lava plains, or maria. This difference in crustal thickness may have stemmed from the Moon's violent birth, from the debris left over after a massive planetary collision, which might have coalesced unevenly around a nascent core. The heavily cratered surface of the far side offered yet another clue. It preserved a record of ancient asteroid bombardments, largely untouched by later volcanic resurfacing, that had smoothed the near side, giving scientists a rare glimpse into the early solar system's turbulent history. The technological hurdles overcome by Luna 3 were equally impressive. In the 1950s, sending a spacecraft to the Moon and successfully photographing its far side was an enormous challenge. The mission required developing film that could survive the vacuum of space, scanning the images and transmitting them across hundreds of thousands of miles to Earth. A feat of engineering that was extraordinary for its time. Every detail, from the reliability of the spacecraft's components to the performance of its propulsion system and the precision of its orbit, offered lessons for the future. These early experiments in deep space communication, even with their imperfections, laid the groundwork for more advanced systems in later robotic missions and eventually human spaceflight. Luna 3's triumph was not just about sending back the first pictures, it proved that complex robotic exploration of other worlds was possible. It was a small step for a spacecraft, but a giant leap for humanity's understanding of its nearest celestial neighbour. The Moon's hidden side was no longer a complete mystery. Its shadowed landscapes, once entirely invisible, had begun to emerge from the darkness, blurry at first but unmistakably real. Humanity had taken its first tentative look at a world that had long been just out of reach, and in doing so had opened the door to countless discoveries yet to come. The middle of the 20th century was a time of fierce rivalry between nations, dominated by the tense standoff known as the Cold War between the United States and the Soviet Union. This competition was not confined to the Earth. It reached far beyond, into the vast, uncharted expanse of outer space. The spark that ignited America's full-scale commitment to exploring the heavens, and that eventually led to the creation of its civilian space agency, came on a crisp autumn day in October of 1957. On that day, the Soviet Union achieved a historic milestone. It successfully launched Sputnik 1, the very first artificial satellite to orbit the Earth. This tiny metallic sphere, which emitted a steady rhythmic beep as it circled the planet every 96 minutes, sent shockwaves across the United States. Sputnik was far more than just a technological triumph. It was a vivid demonstration of Soviet scientific skill and military might. The event, soon labelled the Sputnik Crisis, stirred fear, urgency and determination among American officials and the general public alike. Suddenly, it became painfully clear that the United States could no longer afford to lag behind in this new cosmic race. Before Sputnik's dramatic entrance into orbit, space-related research in the United States was scattered and uncoordinated. Different branches of the military, the Army, the Navy and the Air Force, were all developing rocket technology independently, primarily for ballistic missile programs. Civilian research existed as well, often led by the National Advisory Committee for Aeronautics, or NACIA, which had been established in the early 1900s to study aviation. Yet there was no single, unified civilian agency dedicated to exploring space for peaceful, scientific purposes. The Soviet success made one thing abundantly clear. The United States needed a coordinated, centralized approach if it was to compete effectively in this new frontier. Fragmented efforts had led to duplication of resources and inefficient coordination, leaving the nation seemingly behind in the opening stages of the space race. Recognizing both the strategic and scientific urgency, President Dwight D. Eisenhower acted decisively. He understood that the American response needed to be strong, well-organized, and clearly aimed at peaceful exploration, rather than solely military applications. On the 29th day of July in 1958, President Eisenhower signed the National Aeronautics and Space Act into law. This historic legislation officially created the National Aeronautics and Space Administration, better known as NASA. The agency was given a clear mission: to organize and conduct aeronautical and space activities for peaceful purposes in a way that would benefit all of humanity. This marked a crucial distinction from the Soviet program, which was closely intertwined with military objectives, even though both nations had initially built their space programs on missile technology. NASA was constructed on the solid foundation of ENAC, which ceased to exist as a separate entity. ENAC's highly trained engineers, scientists, and its well-established research facilities became part of NASA, giving the new agency an immediate and substantial technical workforce. In addition, other civilian and military research organizations were incorporated into NASA, including the Jet Propulsion Laboratory, or JPL, and parts of the Army Ballistic Missile Agency. This consolidation brought together a wide range of talent and resources under a single roof, providing the infrastructure and expertise necessary for ambitious space projects. NASA was designed to be agile and responsive, capable of managing massive, complex missions that would push both technology and human endurance to their limits. Its initial goals were not modest. The agency quickly moved from simply launching satellites to putting humans into orbit, and ultimately to sending them to the moon. NASA's early lunar ambitions were carefully planned and progressively challenging. The first step in human spaceflight was Project Mercury, launched in the early 1960s. Mercury's primary mission was to determine whether humans could survive and function in the harsh, weightless environment of space. Astronauts travelled alone in small capsules, orbiting the Earth for short durations. These missions were essential for testing life support systems, studying the effects of weightlessness on the human body, and developing procedures for launch, orbital flight, and safe return. The success of Project Mercury, which included Alan Shepard's suborbital flight and John Glenn's orbital flight, proved that humans could operate effectively in space, laying both practical and psychological foundations for more complex missions. Building on Mercury's achievements, NASA launched Project Gemini in the mid-1960s. These two-person missions were designed to develop the advanced skills needed for a moon landing. Gemini astronauts practiced crucial maneuvers, including orbital rendezvous and docking, which would later allow the lunar module to link with the command module in lunar orbit during Apollo missions. They also performed spacewalks, testing their ability to work outside the spacecraft in the vacuum of space. Gemini missions lasted longer than Mercury flights, providing valuable data on human endurance over extended periods. In total, 12 Gemini flights perfected the techniques and procedures that would become essential for the journey to the moon. All of this preparation led to Project Apollo, NASA's most ambitious undertaking, landing humans on the moon and bringing them safely back to Earth. In 1961, President John F. Kennedy issued a bold challenge to land a man on the moon before the end of the decade. This clear, daring goal galvanized the nation and set NASA on an ambitious path. Before humans could safely touch the lunar surface, however, detailed information about the moon was needed. NASA's early robotic missions, particularly the Ranger and Surveyor programs, acted as precursors. These uncrewed spacecraft served as scouts, mapping the lunar terrain, studying its geology, and providing the critical intelligence necessary to make human landings possible and safer. The Ranger program marked NASA's very first series of uncrewed attempts to get up close, detailed images of the moon's surface. Launched during the early to mid-1960s, these missions had a simple yet daring goal: to fly directly toward the moon and send back high-resolution television images to Earth, right up until the moment they intentionally crashed into the lunar surface. The early Ranger missions were not without hardship. Many faced technical setbacks and outright failures, a painful but essential part of learning to explore deep space in an era when humanity was just beginning to reach beyond Earth. Problems range from power system failures to instruments that simply would not function as intended. Each disappointment, however, became a valuable lesson, helping engineers refine their designs and perfect their procedures for the missions that followed. Perseverance finally bore fruit with Ranger 7. Launched in July of 1964, this mission was a stunning success. As Ranger 7 hurtled toward the moon, it transmitted more than 4,300 high-resolution images, revealing features far smaller than anything that Earth-based telescopes could capture. Craters as tiny as 1 foot across appeared in astonishing clarity, giving scientists an unprecedented close-up view of the lunar landscape. Following this success, Ranger 8 took off in February of 1965, and Ranger 9 followed in March of 1965. Both missions continued the legacy, sending thousands of detailed images of the moon's surface. These pictures played a crucial role in resolving a major scientific debate of the time. Was the moon's surface covered by a soft, deep layer of dust that could swallow a landing spacecraft, or was it firm enough to support one? The images clearly showed a solid, rocky terrain densely dotted with craters, perfectly capable of bearing the weight of a lander. This information was absolutely vital for designing the Apollo lunar module's landing gear and for selecting safe landing zones. Beyond landing safety, the images also offered insights into the lunar regolith, the loose, fragmented material covering the Moon and allowed scientists to study the effects of micrometeorite impacts on its surface. Building on the success of the Ranger impact probes, NASA then launched the Surveyor program, which represented a monumental step forward in lunar exploration. The goal of the Surveyor missions was far more ambitious than merely crashing into the Moon. They aimed for soft landings, allowing spacecraft to touch down gently and examine the lunar surface directly. Each Surveyor was equipped with a retro-rocket system designed to slow its descent, ensuring a controlled and safe landing. These spacecraft were also far more sophisticated, carrying multiple television cameras for both panoramic and close-up views, as well as instruments to analyze the Moon's soil. Surveyor 1 achieved a historic milestone in June of 1966, making the first successful American soft landing on the Moon. This triumph demonstrated that NASA could safely land a spacecraft on another celestial body. Surveyor 1 transmitted more than 11,000 images of its landing site, revealing the lunar landscape in extraordinary detail. Over the next several years, a total of 7 Surveyor spacecraft were launched, 5 of which successfully touched down. Each mission provided crucial data. For instance, Surveyor 5 carried an alpha scattering instrument that analyzed the Moon's chemical makeup, confirming that the soil was basaltic, much like volcanic rocks on Earth. Other surveyors had scoops that dug small trenches in the lunar regolith, providing direct evidence of the soil's strength and consistency. These findings confirmed that the lunar surface could support the Apollo lunar module, and that astronauts could walk across it without sinking. The detailed images and measurements from the Surveyor missions also helped engineers understand the sizes of rocks, boulders, and terrain features that future astronauts would face, allowing for vital adjustments in both mission planning and astronaut training. In many ways, the Surveyor program served as the ultimate rehearsal and validation for the Apollo landings. In addition to Ranger and Surveyor, NASA initiated the Lunar Orbiter program in the mid-1960s. While some of its detailed mapping of the Moon's far side would be covered in later explorations, it is important to recognize its role as one of America's first systematic lunar reconnaissance missions. The lunar orbiters were designed to map the entire lunar surface, both near and far sides, with high resolution. Their main goal was to photograph potential Apollo landing sites, ensuring that selected locations were flat, free of large boulders, and safe for human exploration. The Lunar Orbiter missions produced a comprehensive photographic atlas of the Moon, revealing the intricate details of craters, rills, and mountains across its entire surface. Together with the data from Ranger and Surveyor, these images provided an unparalleled understanding of the lunar environment, knowledge that proved absolutely indispensable for the daring Apollo program and humanity's first steps on another world. For countless generations, the Moon has revealed only one of its faces to humanity. This is because of a phenomenon known as tidal locking, which ensures that the same side of the Moon perpetually turns toward Earth. For all of human history, until the age of space travel, the far side of the Moon remained an uncharted mystery, completely hidden, a silent hemisphere known only through imagination, speculation, and scientific theorizing. Yet, with the dawn of the Apollo program led by the National Aeronautics and Space Administration, or NASA, humans not only gained the ability to orbit the Moon, but eventually to set foot upon its familiar near side. As astronauts circled this celestial body, they were granted a first-ever glimpse of the Moon's hidden hemisphere, allowing humanity to supplement the robotic data collected by earlier probes with the irreplaceable perspective of human eyes. The first mission to carry people around the Moon was Apollo 8. Launched in December of 1968, Apollo 8 was bold and highly accelerated, a mission originally planned merely as a test flight in Earth orbit for the Apollo Command and Service modules. However, in a daring strategic decision, NASA sent the crew of Frank Borman, James Lovell, and William Anders on a direct journey to the Moon. Their task was to complete 10 lunar orbits before returning safely to Earth. For the first time in history, human eyes would behold the far side of the Moon directly. As the spacecraft crested the lunar limb, the Earth slipped out of view, and the previously hidden hemisphere unfolded before them. The astronauts' experience was profound, and their live television broadcasts allowed millions of people on Earth to share in the wonder, even if the images were grainy and limited by the technology of the day. On their initial pass around the Moon, The crew was struck by the stark contrast between the far side and the familiar near side. They immediately noticed the absence of the dark volcanic plains, or maria, which dominate the Earth-facing side. Instead, the far side stretched endlessly as a rugged, heavily cratered landscape. William Anders famously described it as an immense, forbidding, lonely expanse. Its surface appeared a desolate grey, churned and pockmarked by billions of years of meteor impacts. These direct human observations confirmed, with far greater nuance, what the Soviet Lunar 3 robotic probe had first glimpsed in 1959. Unlike early cameras, human vision could perceive depth, subtle variations, and scale, conveying the overwhelming desolation of this hidden lunar world. Astronauts described craters within craters, a testament to a relentless, ancient bombardment that had shaped the moon over eons. Passing over the far side brought more than visual marvels. It also enforced silence. As the Apollo spacecraft moved behind the moon, all communication with Earth ceased. For approximately 15 to 20 minutes during each orbit, Apollo 8's crew, and those of all later missions, were entirely cut off from mission control in Houston. This communication blackout underscored the vast distance from home and the stark isolation of their journey. Frank Borman, the mission commander, later reflected that during these periods, they truly felt alone in the universe. The spacecraft relied solely on its systems and the vigilance of its crew. All updates, telemetry and instructions paused until the moment the moon's limb allowed the line of sight to reconnect. Though mission control could precisely predict the blackout's duration, for the astronauts, it was a profound experience of self-reliance and solitude. Apollo 10 followed in May of 1969, serving as a dress rehearsal for the first lunar landing. This mission carried the full Apollo stack, including a lunar module that separated and descended to within 50,000 feet of the lunar surface before returning to the command module. The crew, Thomas Stafford, John Young and Eugene Cernan, also orbited the moon extensively, offering further observations of the far side. While their main focus was scouting potential landing sites on the near side, multiple passes over the far side allowed them to confirm its uniform, cratered, ancient character. They noted craters of immense size, some spanning hundreds of miles, and the dramatic contrast between sunlit crater rims and deep-shadowed interiors. Each orbit revealed new perspectives, highlighting the intricate topography and the moon's silent grandeur. Apollo 11, the historic mission that first carried humans to the lunar surface in July of 1969, also added crucial human observations of the far side. While Neil Armstrong and Buzz Aldrin descended to the moon in the lunar module Eagle, Michael Collins remained in orbit aboard the command module Columbia. For nearly 28 hours, Collins circled the moon alone, completing 30 orbits and passing repeatedly over the far side. His experience provided a singular perspective on the moon's scale and isolation. Collins described the far side as uniformly pockmarked, radiating a profound sense of loneliness, with the recurrent communication blackouts emphasizing the absolute solitude of orbit. His detailed observations reinforced earlier robotic and human reports, adding the essential human element to scientific understanding. Collins' reflections on seeing the familiar Earth vanish and the unknown lunar terrain appear remain poignant testaments to the psychological depth of exploring another world. Subsequent Apollo missions, Apollo 12, 14, 15, 16 and 17, continued to expand human knowledge of the moon's far side during their orbital phases, though the primary objectives increasingly focused on detailed scientific exploration of near-side landing sites. The necessity of lunar orbit meant every crew experienced repeated encounters with the hidden hemisphere. On later missions, mapping cameras and instruments housed in the service module's Scientific Instrument Module, or SIMBay, systematically collected data over the far side. Yet the first-hand impressions of astronauts remained invaluable, offering perspective, scale, and a uniquely human understanding that complemented the instruments and robotic probes alike. The accounts from the later Apollo missions repeatedly highlighted the rugged, ancient character of the moon's far side. Astronauts such as David Scott of Apollo 15, John Young of Apollo 16, and Eugene Cernan of Apollo 17, each of whom had flown on multiple missions and had extensive experience orbiting the moon, often remarked on the stark, raw landscape of the far side. In contrast to the near side, which displayed a variety of geological features, the far side appeared harsher, more battered, and dramatically uneven. From their vantage point, they could identify higher plateaus, deep basins, and the rough texture of the surface, providing a kind of qualitative topographic map with their own eyes. The angle of sunlight played a crucial role in these observations. When the sun hung low along the lunar horizon, long shadows stretched across craters and mountains, making the topography strikingly clear. At midday, when the sun shone more directly, the terrain seemed flatter, but differences in the reflectivity of the lunar soil or regolith became more noticeable. A recurring and defining feature of all Apollo missions was the communication blackout that occurred whenever the spacecraft passed over the moon's far side. Because radio signals could not travel through the moon, astronauts were completely out of contact with mission control for these stretches. This required careful preparation and strict adherence to protocols. Just before entering the blackout zone, mission control would send final instructions, updates, and reminders. During the blackout, astronauts relied entirely on their onboard computers, instruments, and their own training. These periods were sometimes used for quiet reflection, or for tasks that did not require immediate guidance from Earth. The moment the spacecraft emerged from behind the moon, and contact was regained, always brought relief, a confirmation that everything was proceeding according to plan. For the crews, these brief intervals of enforced isolation highlighted the vastness of space and the delicate interplay of technology keeping them tethered to Earth. They also underscored the critical importance of the command service module as a fully self-contained life support system. The training that prepared astronauts for lunar missions was extensive. It included detailed simulations and thorough geological briefings. While much of the focus was on the planned landing sites on the near side, astronauts also studied what little was known of the far side from early robotic probes. This background allowed them to make informed, careful observations while orbiting the moon. They were trained to search for particular geological features even when seeing them for the first time. Their direct observations, whether shared live or recorded for later review, provided invaluable human confirmation of robotic mapping. Details such as the density of craters, the presence or absence of certain terrains, and the texture of the lunar surface all added depth to the scientific record. The human eye and mind, capable of instantly synthesizing complex visual information, gave a richness of understanding that early photographic equipment alone could not provide. The perspective of the command module pilot, the astronaut who remained in orbit while two crewmates descended to the lunar surface, was especially unique when it came to the far side. Michael Collins on Apollo 11, Richard Gordon on Apollo 12, Al Worden on Apollo 15, Ken Mattingly on Apollo 16, and Ronald Ron Evans on Apollo 17 all spent significant periods alone, circling the moon multiple times. Their solitude added an intense, introspective quality to their observations. For hours, sometimes days, they were the only humans directly witnessing the sweeping panorama of the far side. In post-mission books and interviews, they described this alien landscape in rich detail. The eerie silence, the absence of anything resembling life or recent geological activity, and the overwhelming sense of ancient time etched into the battered surface. Even Apollo 13, the mission that famously suffered a catastrophic in-flight emergency, offered a dramatic encounter with the far side. After an explosion crippled the service module, astronauts James Lovell, Jack Swigert, and Fred Hayes were forced to rely on a free return trajectory, using the moon's gravity to swing their damaged spacecraft back toward Earth. As they passed behind the moon, over the far side, all contact with mission control was lost. What was normally a routine blackout became a tense, anxiety-filled ordeal as they silently circled the hidden hemisphere, unsure if their spacecraft would survive the journey home. While their focus was survival rather than scientific observation, their experience starkly illustrated the isolating nature of the far side and the critical importance of dependable communication. The sum of human observations from all the Apollo missions dramatically expanded humanity's understanding of the moon's far side. Astronauts added a human dimension to the precise measurements of robotic probes. Instruments could measure elevation, composition, and other physical characteristics with exactness. But only a human observer could convey the feel, the impression, of standing, or orbiting, above such an ancient and forbidding terrain. their accounts consistently reinforced the scientific conclusion that the far side was fundamentally different from the near side, older, heavily cratered, and lacking the extensive volcanic resurfacing seen on the Earth-facing side. These observations helped explain the Moon's asymmetry, supporting theories related to variations in crust thickness and the history of impacts. Slowly, the far side, once entirely hidden, revealed its secrets to the persistent gaze of human explorers, enriching our understanding of Earth's nearest celestial neighbour. The legacy of their observations continues to shape our knowledge of the Moon, turning what was once a mysterious shadowed world into a well-studied and vividly imagined landscape. The Moon bears the scars of a violent and ancient past. Its surface is pockmarked with countless craters, each one a silent witness to the collisions that shaped the early solar system. These craters vary enormously in size, from tiny dimples barely noticeable to massive basins stretching hundreds of miles across. Among them, one stands above all others for its sheer scale and significance, the South Pole Aitken Basin, often called SPA. This colossal structure, lying on the Moon's far side, is not only the largest and deepest confirmed impact basin on the Moon, but it also ranks among the largest and oldest known impact features in the entire solar system. Its immense size, mysterious location, and scientific potential have made it a prime target for exploration by NASA and other space agencies. SPA holds vital clues about the Moon's formation, its internal layers, and the violent bombardment history of the early solar system. The South Pole Aitken Basin was not uncovered all at once. Instead, its existence became clear slowly as successive robotic missions brought back more and more detail. The first hints appeared in October of 1959 when the Soviet Union's Lunar 3 spacecraft transmitted blurry images of the Moon's far side. Though these early pictures were low in clarity, they revealed a heavily cratered landscape strikingly different from the side that faces Earth. In the mid-1960s, NASA launched the Lunar Orbiter program, sending a series of orbiters around the Moon that returned higher-resolution photographs of the far side. These images allowed scientists to begin mapping a vast, subtle depression, gradually revealing the outline of SPA. Later, cameras aboard the Apollo missions provided even more detailed images, confirming the basin's truly gigantic scale. Still, the basin's full depth and extent remained difficult to grasp from photographs alone, especially because the low-angle sunlight at the lunar poles cast long shadows that obscured its features. The basin's name reflects its location. It surrounds the Moon's south pole and stretches northward toward the Aitken crater, a prominent landmark near the basin's northern boundary. Its shape is roughly circular, sometimes slightly elliptical, a reflection of the angle at which the enormous impactor struck. The dimensions of SPA are staggering. It spans about 2,500 kilometers, or roughly 1,550 miles, from rim to rim. To put this in perspective, that is roughly the distance from New York City to Dallas. Its depth is equally impressive, ranging from 8 to 13 kilometers, or 5 to 8 miles, from the highest edge down to the deepest floor. In comparison, the Grand Canyon on Earth is tiny. SPA represents a truly monumental excavation of the Moon's crust. The age of the South Pole Aitken Basin adds to its importance. Scientists estimate that it formed very early in the Moon's history, likely between 4.3 and 4.2 billion years ago. This places the impact during the period known as the Late Heavy Bombardment, a hypothesized era in the early solar system when a large number of asteroids and comets pummeled the inner planets and their moons. Being both ancient and enormous, SPA serves as a key geological marker, providing scientists with a reference point for understanding lunar history and the bombardment history of the entire solar system. By studying it, researchers can gain insight into the conditions and events that shaped planets and moons in their earliest years. NASA's exploration efforts have been crucial in uncovering the secrets of SPA. Early missions brought photographic evidence, but more advanced instruments were needed to understand its composition and structure. In the early 1990s, the Galileo spacecraft, on its way to Jupiter, performed a flyby of the Moon and gathered multispectral imaging data, revealing new information about the basin. Soon after, the Clementine mission, launched in 1994, produced detailed high-resolution photographs and topographic maps, along with multispectral data that helped define SPA's unique mineral makeup. A particularly important mission was NASA's Lunar Prospector, launched in 1998. Equipped with a gamma-ray spectrometer, it mapped the elemental composition of the lunar surface. For the South Pole Aitken Basin, it revealed unusual concentrations of elements such as iron and titanium on the basin floor. Scientists interpreted this as evidence that the colossal impact had dug deep into the moon's crust, possibly even reaching the mantle, and brought this material closer to the surface. Lunar Prospector also measured the moon's gravity in the area, confirming the basin's massive size and revealing its unique subsurface structure. The most detailed information about SPA comes from NASA's Lunar Reconnaissance Orbiter, launched in 2009 and still operating today. LRO has transformed our understanding of the moon, including SPA, thanks to its suite of advanced instruments. Its Lunar Orbiter Laser Altimeter, or LOLA, mapped the basin's surface with unmatched precision. By sending laser pulses to the lunar surface and measuring how long it took for them to return, LOLA created a three-dimensional map of SPA. Scientists could now see the basin's depth, rim, and floor contours with incredible accuracy. These measurements allowed researchers to calculate the volume of lunar material excavated by the impact, providing essential data for understanding how such enormous basins form. NASA's Lunar Reconnaissance Orbiter carried an important instrument called the Diviner Lunar Radiometer Experiment. This device measured temperatures across the moon's surface, revealing how different areas absorb and radiate heat. By understanding these thermal properties, scientists could also make educated guesses about the minerals present in the lunar soil. When these temperature maps were combined with data from other orbiting spectrometers, researchers were able to create increasingly detailed compositional maps of the South Pole Aitken Basin, or SPA. These maps consistently showed that the floor of SPA contains rock rich in iron and magnesium, elements normally found deep in the moon's mantle, the layer lying beneath the crust. This discovery strongly supports the idea that the SPA impact was so massive and powerful that it punched through the moon's crust, exposing material from its deep interior. For scientists, this is an extraordinary opportunity, as it allows them to study the moon's mantle directly without having to drill miles down into the surface. The story of how the South Pole Aitken Basin formed is equally fascinating. The leading theory proposes that SP was created by the collision of an enormous asteroid or comet, possibly hundreds of kilometers across, moving at extraordinary speed. The energy released during this event would have been almost unimaginable, far surpassing any explosion ever witnessed on Earth in recorded history. Such a collision would have instantly vaporized vast amounts of rock, melted even more, and hurled enormous quantities of debris across the lunar surface and into space. The crater formed by this impact was so enormous that its rim would have immediately begun collapsing inward, forming the multi-ringed structure that is typical of such giant basins. Over billions of years, however, subsequent impacts have worn down and softened much of this original structure. One major effect of the SPA impact is that it left the moon's crust thinner beneath the basin floor. Scientific models suggest that the collision stripped away a large portion of the original crust, leaving a thinner and warmer layer at the base of SPA. Interestingly, despite this thinning, the basin does not contain the vast volcanic plains, or mare basalts, that are common on the moon's near side. Although small, patchy mare deposits exist within SPA, they are far less extensive or voluminous than those found in basins like Mare Imbrium or Mare Serenitatis. This has sparked lively scientific debate. One explanation is that the impact occurred at a time when the moon's interior was not ready to produce large-scale volcanism. Another idea is that the mantle rocks exposed by the impact were not suitable for forming widespread lava flows, or that the erupted material was simply too thick and sticky to spread over large areas. The hypothesis that SPA brought up mantle material is central to its scientific importance. If true, the basin acts as a natural laboratory, giving scientists direct access to the moon's deep interior. Researchers are especially eager to confirm the presence of untouched mantle rocks, because these could reveal the moon's composition below the crust. Minerals such as olivine and pyroxene, which are commonly found in Earth's mantle, would be strong indicators that mantle material has been exposed. Data from LRO and other orbiters already suggest these minerals exist in SPA, but analysing actual samples would provide definitive proof. Understanding the mantle is crucial for learning about the Moon's thermal history, its ancient magnetic field, and how it's separated into different layers. The SPA impact may also help explain the differences observed between the Moon's near and far sides. The enormous energy released and the massive redistribution of mass likely altered the Moon's gravitational field and internal stresses. Some models even suggest that the impact could have shifted the Moon's centre of mass, or changed how heat moved within its interior. These changes may have contributed to variations in crustal thickness, and to the uneven distribution of volcanism between the two hemispheres. The heat from such a gigantic impact would have lasted millions of years, potentially influencing volcanic activity and the evolution of the Moon's core. The scientific importance of the South Pole Aitken Basin is vast. First, it offers a rare window into the early solar system. Its ancient age and enormous size make it a key site for understanding the late heavy bombardment, a period when the inner planets were pummeled by countless asteroids and comets. By studying craters within SPA and along its rim, scientists can refine models of early solar system dynamics and the population of celestial impactors that shaped our planetary neighbourhood. Second, SPA provides unparalleled access to the Moon's deep interior. Collecting and analysing samples from the basin would be a scientific treasure, allowing researchers to test theories about the mantle's composition and the Moon's overall internal layering. Third, SPA includes parts of the lunar South Polar region, an area of immense interest because of confirmed water ice in permanently shadowed craters. While the ice itself was not caused by the SPA impact, the basin's geography means that many of these cold traps lie within its vast expanse. Instruments aboard LRO, such as Lola, have mapped these shadowed regions in remarkable detail, confirming the presence of significant quantities of water ice. This discovery is crucial for future human exploration. Water ice could be converted into drinking water, breathable oxygen, and rocket fuel, making a sustained human presence on the Moon far more feasible. In this sense, the South Pole Aitken Basin is not just a scientific goldmine, but also a strategic location for future lunar missions. Exploring the South Pole Aitken Basin is no small feat, and comes with a host of formidable challenges. Nestled on the Moon's far side, this immense basin is hidden from direct view from Earth, which means that any lander or rover venturing into its depths cannot communicate with our planet in the usual way. Instead, these machines must rely on relay satellites orbiting the Moon to send their precious data across the void of space. The landscape itself adds to the difficulty. Enormous craters pockmark the terrain, steep slopes rise and fall abruptly, and vast regions are shrouded in deep, unbroken shadow. Navigating such rugged terrain is a tremendous test for any robotic mission. Adding to the danger, some of these shadowed regions never see sunlight and rank among the coldest spots in the entire solar system, with temperatures plunging to hundreds of degrees below 0 Fahrenheit. Operating machinery in such extreme cold demands cutting-edge technology, powerful energy systems, and engineering designed to withstand relentless freezing conditions. Yet, despite these hurdles, the scientific allure of the South Pole Aitken Basin is irresistible. Around the world, researchers and space agencies are increasingly focusing their attention on this mysterious lunar frontier. A striking example is China's Chang'e 4 mission, which, in January of 2019, achieved the historic first soft landing on the Moon's far side. Its rover, Yutu-2, rolled onto the surface of the von Karman crater, located within the vast expanse of the South Pole Aitken Basin. Though this was not a NASA mission, its success proved that operating in this extreme environment was possible and highlighted the international fascination with this extraordinary geological treasure. Looking ahead, NASA and other space agencies have their sights set on further exploration of SCPA, with plans for both robotic and potentially human missions. Among the most exciting goals are sample return missions, which would bring actual fragments of the basin back to Earth for detailed laboratory study. These samples could reveal unprecedented secrets about the Moon's origin and offer invaluable clues about the earliest days of our solar system. Every mission, every measurement, and every carefully collected rock from SPA brings humanity a step closer to unravelling the ancient stories etched into this immense shadowed basin. The South Pole Aitken Basin, with its extreme environment and ancient mysteries, continues to challenge explorers while offering a scientific treasure trove unlike any other. The Moon carries upon its surface a remarkable record of billions of years of cosmic collisions. Its face is covered with countless craters, each formed when asteroids, comets, or smaller meteoroids struck with immense force. Unlike Earth, which is alive with wind, rain, rivers, and the slow movement of tectonic plates that continually reshape and erase its ancient scars, the Moon is a quiet, unchanging world. There are no rains to wash away its marks, no winds to wear down its ridges, and no active volcanoes to cover up its history. Because of this, the Moon serves as a cosmic archive, preserving the story of impacts almost from its very birth, nearly 4.5 billion years ago. Yet these craters are not spread evenly across the Moon's surface. One of the most striking differences lies between the side that always faces Earth, the near side, and the side that remained hidden from human eyes until the dawn of space exploration, the far side. NASA's careful exploration of the Moon has revealed this dramatic difference and helped explain why the two hemispheres tell such different geological stories, offering profound insights into both the Moon's own history and that of the inner solar system. Looking up at the Moon from Earth, even with just the naked eye, we can see two very distinct types of terrain. The first are the bright, rugged highlands, heavily pockmarked with craters. The second are the darker, smoother plains known as Maria, a word meaning seas in Latin. Early astronomers once believed these dark patches were actual bodies of water, but we now know they are enormous basins filled with basaltic lava that flowed billions of years ago, creating flatter, less cratered regions. These lava flows resurfaced large areas of the near side, effectively hiding or filling in many of the older craters. Over time, this process has given the near side a somewhat smoother, more uniform appearance, though the highlands still preserve countless impact scars. The far side of the Moon, however, looks very different. The first robotic probes, later confirmed by human observations during the Apollo missions and by detailed maps from NASA spacecraft, revealed a landscape almost entirely covered by heavily cratered highlands. Large Maria are rare on this side, so craters dominate the scenery, ranging from tiny pits to vast multi-ringed basins. It is an ancient, endlessly pockmarked expanse, far more densely cratered than the near side. Where the near side offers patches of smooth, dark plains, the far side presents an unbroken tapestry of impact scars, a clear visual reminder of billions of years of bombardment. This striking contrast is one of the Moon's most fundamental features. NASA's missions have provided compelling explanations for this asymmetry. The key factor lies in the thickness of the Moon's crust. Detailed studies, including measurements from the Lunar Prospector in the late 1990s and the Lunar Reconnaissance Orbiter, launched in 2009, show that the far side's crust is much thicker than that of the near side. On average, the far side is about 60 kilometers, roughly 37 miles, thick, while the near side averages only about 30 kilometers, or approximately 18.5 miles. This difference has had a profound effect on how the Moon evolved, and how easily volcanic activity could reshape its surface. This uneven crust likely formed very early in the Moon's history, perhaps during its very creation. One leading idea, known as the giant impact hypothesis, suggests that the Moon formed from debris blasted into orbit after a Mars-sized body collided with the young Earth. As this molten debris cooled, the Moon's crust developed unevenly, influenced by gravity, tidal forces from Earth, and perhaps uneven internal heating. Whatever the exact cause, this early asymmetry set the stage for how the two hemispheres would develop over billions of years. The thickness of the crust directly affected volcanic activity. On the near side, the relatively thin crust allowed molten lava from the Moon's interior to rise more easily to the surface. These lava flows filled large impact basins, forming the dark Maria that we see today and covering up many older craters. On the far side, the thick crust acted as a barrier. Even when enormous impact basins like the colossal South Pole Aitken Basin were formed, volcanic lava could not easily reach the surface to fill them. As a result, most of the far side's craters remained untouched, preserved for billions of years. The far side, therefore, tells a story of ancient bombardments almost entirely undisturbed, while the near side shows a landscape partially shaped and smoothed by volcanic activity. Another factor that contributes to the Moon's unevenness, and one that NASA missions have helped to find, is the uneven spread of certain heat-producing radioactive elements inside the Moon's crust and mantle. Data from Lunar Prospector's gamma-ray spectrometer showed a clear concentration of these elements, especially potassium, uranium and thorium, together called CREEP, which stands for potassium, rare earth elements, and phosphorus, on the near side of the Moon, mainly in a region called the Procellarum creep terrain. These radioactive elements give off heat as they break down. Their higher amount on the near side would have kept the mantle underneath warmer and more molten for longer times, helping the widespread volcanic eruptions that created the Maria. The lower amount of these heat-producing elements on the far side meant that its interior cooled faster, leading to less volcanic activity and, as a result, less resurfacing of its old cratered land. This uneven spread of internal heat sources played an important role in shaping the very different geological histories of the Moon's two sides. The way NASA discovered these important differences involved a series of increasingly advanced missions. The first visual confirmation of the far side's heavily cratered surface came from the Soviet Union's Luna 3, but NASA's Lunar Orbiter program in the mid-1960s gave much higher resolution and more systematic photographic coverage. These photo missions, mainly designed to scout possible landing sites for the Apollo program, photographed both the near and far sides of the Moon in detail. The photos clearly showed the many highlands and the lack of Maria on the far side, giving the first full visual proof of the sharp contrast. After these visual surveys, later NASA missions used more advanced instruments to measure these differences. The Clementine mission in 1994, for example, carried a laser altimeter that carefully measured the Moon's shape and heights, allowing detailed maps of the elevations and depths across the whole surface, including the far side. This data showed the higher average height of the far side highlands compared to the near side. Lunar Prospector, launched in 1998, was important for mapping the Moon's gravity and elemental makeup. Its gravity mapping showed distinct mass concentrations called mascons, mainly linked to the large mare basins on the near side, which are dense lava flows. The far side, without these large mare basins, also lacked these strong mascons, further showing its different underground structure. Lunar Prospector's gamma-ray spectrometer gave the key data on the uneven spread of radioactive elements, directly connecting them to differences in internal heat and volcanism. The Lunar Reconnaissance Orbiter, or LRO, launched in 2009, has probably given the most detailed and complete data on the Moon's cratered surface and the differences between its two sides. LRO's Lunar Orbiter, laser altimeter or LOLA, mapped the Moon's surface with great precision, making very accurate three-dimensional models. This let scientists measure the depths and widths of craters and basins on both sides with unmatched accuracy, clearly showing the higher number of impact features on the far side. LRO's Lunar Reconnaissance Orbiter camera, or LROC, has taken millions of high-resolution images, showing fine details of individual craters, the debris around them, and the wide spread of cratering on the far side. Also, LRO's Diviner Lunar Radiometer experiment has made detailed heat maps, giving clues about surface materials and supporting ideas about differences in heat flow and crust properties. The meaning of these differences in cratering is very important for understanding how the Moon changed over time. The unevenness tells a complex story of how internal geological processes, driven by uneven heat, work together with external impacts over billions of years. The far side, with its thicker crust and lower amount of heat-producing elements, kept an older record of the Moon's surface. This makes it a unique place to study the early heavy bombardment period of the solar system, called the Late Heavy Bombardment. This period, thought to have happened around 4.1 to 3.8 billion years ago, saw a big increase in the number of impacts on the inner planets and their moons. The far side's heavily cratered highlands keep a more original, less changed record of these old impacts, letting scientists check cratering models and understand the asteroids and comets that hit the early solar system. Counting craters is a basic method used by planetary scientists to figure out the relative ages of planetary surfaces. A surface with more craters is usually considered older because it has been hit for a longer time. By comparing the heavily cratered far side with the less cratered Maria of the near side, scientists can make a relative timeline for different parts of the Moon. When combined with absolute age dating from lunar samples brought back by the Apollo missions, the cratering record from both sides helps build a full timeline for lunar geological events. This method is then used to date surfaces on other airless bodies in the solar system, like Mercury and Mars, where no samples have been brought back yet. So, the Moon's cratered surface, especially the preserved record on the far side, acts as a key benchmark for dating surfaces across the solar system. Studying the Moon's two different cratered sides also helps scientists understand the bigger history of the solar system. By looking at the sizes, spread, and worn-down state of craters on both sides, scientists can learn about the objects that hit the early solar system. This helps piece together the chaotic conditions during the formation and early growth of planets. The Moon's preserved cratering record is very valuable because Earth's own old impact craters have mostly been erased by erosion, volcanism, and moving plates. The Moon therefore acts as an important guide, showing the bombardment history that Earth must have experienced. Looking ahead to future exploration, the far side's old, heavily cratered surface brings both challenges and unique scientific chances. Its rugged land makes landing and moving around harder for robots and humans. However, because it is old and mostly unchanged, it offers pure targets for sample return missions that could give access to the oldest Moon materials. Such samples could give clear answers about the Moon's early formation and the early solar system. Also, the far side's natural shielding from Earth's radio signals makes it a great place to build radio telescopes, offering a unique view of the universe, especially for faint signals from the early cosmos, free from Earth interference. The Moon's two very different cratered worlds, near and far, continue to provide exciting scientific discoveries, driven by NASA's ongoing exploration. The Moon's surface can be seen as a tale written in stone, divided into two very different kinds of terrain. There are the dark, relatively smooth plains known as Maria, and then there are the brighter, rough, and heavily cratered regions called highlands. Among these, the highlands are the most widespread, covering the majority of the Moon's surface, and they dominate the far side, the hemisphere hidden from Earth. These highlands are far more than just hills and valleys. They are immense geological time capsules preserving the Moon's earliest history. Their age, makeup, and the countless craters peppering them tell a story of the Moon's birth, its initial internal separation into layers, and the violent cosmic conditions that shaped the early solar system. Over decades, NASA's robotic and human missions have helped unlock these stories, revealing clues not only about the Moon's origins, but also about how rocky worlds across the solar system may have formed. The lunar highlands are truly ancient, representing the oldest surviving crust of our celestial neighbour. Scientists estimate that these areas formed during the Moon's very first years, within the first few 100 million years after it came into existence, around 4.5 to 4 billion years ago. By contrast, the dark mare plains are younger, forming later, roughly between 3.8 and 3.2 billion years ago. The birth of the highlands is closely tied to a key theory called the lunar magma ocean hypothesis. According to this idea, shortly after the Moon formed from debris following a giant impact with the early Earth, it was mostly molten, a vast ocean of glowing molten rock and minerals. As this enormous magma ocean began to cool, heavier minerals sank toward the Moon's centre, forming the core and mantle. Lighter minerals, especially plagioclase feldspar, floated to the top, gradually piling up and solidifying over millions of years. This floating material eventually formed a low-density, buoyant crust made primarily of a rock called anorthosite. This primordial crust became the highlands. The process, known as differentiation, separated the Moon into layers according to density, similar to Earth's core, mantle, and crust. But unlike Earth, the Moon's separation was driven largely by the cooling of a global magma ocean, rather than ongoing internal heat and convection. In many places, especially on the far side, the highlands remain untouched by later volcanic activity, making them the Moon's original pristine surface. Perhaps the most striking feature of the lunar highlands is their sheer number of impact craters. From tiny pits invisible to the naked eye to enormous basins stretching hundreds of kilometers, the highlands are completely covered with scars from collisions. These craters are dramatic evidence of a violent chapter in the solar system's history, known as the Late Heavy Bombardment, which occurred roughly 4.1 to 3.8 billion years ago. During this time, asteroids and comets struck the inner solar system at far higher rates than today. Because the highlands had already formed, or were forming during this period, and have remained largely inactive since, they preserve the full record of these ancient cosmic attacks. Over time, newer impacts often overlapped older ones, creating a densely layered, chaotic landscape where it can be difficult to identify individual craters. At a certain point, the highlands become so cratered that adding more impacts doesn't create noticeably more craters, but instead reshapes and wears down the ones already there. The preservation of these ancient craters, particularly on the Moon's far side, is linked to the thickness of the crust and its lack of heat-producing elements. Because the far side's crust is thicker and cooler, it experienced far less volcanic activity than the near side. On the near side, flowing lava filled many ancient craters to form the smooth maria we see today, but the far side's highlands were mostly spared. As a result, these regions accumulated impact scars over billions of years, serving as a frozen snapshot of the Moon's early chaotic youth. The highlands act almost like a fossil record, offering an untouched glimpse of what the Moon once looked like. NASA's decades of lunar exploration have greatly increased our understanding of the highlands' composition. The first direct evidence came from the Apollo missions, which returned rock samples from highland regions near the landing sites or from areas excavated by large impacts. These samples confirmed that the highlands are made mainly of anorthosite, a light-coloured igneous rock composed almost entirely of plagioclase feldspar. Its low density explains why it floated to the top of the molten lunar ocean to form the first crust. Even though Apollo astronauts landed mostly on the near-side Maria, they deliberately collected samples that represented highland material, including debris ejected by impacts. Beyond the rocks brought back by astronauts, NASA's robotic orbital missions have provided detailed data about the Moon's far side. The Clementine mission in 1994 used multispectral cameras to detect the specific patterns of light that indicate anorthosite, confirming its widespread presence. The Lunar Prospector mission, launched in 1998, carried a gamma-ray spectrometer that measured elements on the Moon's surface. Its data showed that the highlands have lower amounts of iron and titanium compared to the mare basalts, consistent with the composition of anorthosite, since these heavier elements are more common in volcanic rocks. Together, these missions have helped paint a complete picture of the highlands as the Moon's ancient original crust, a record of its fiery birth and turbulent early life. The Lunar Reconnaissance Orbiter has dramatically deepened our understanding of the Moon's highlands, their makeup, their structure, and their long turbulent history. One of LRO's key instruments, the Lunar Orbiter Laser Altimeter, known as LOLA, has mapped the highlands' topography with remarkable precision, revealing not only their elevated heights, but also the fine details of their cratered surfaces in ways never seen before. Another instrument, the Diviner Lunar Radiometer Experiment, measured the heat radiating from the Moon's surface, helping scientists identify the types of minerals present based on the unique thermal fingerprints each one produces. Adding to this treasure trove of data, the Lunar Reconnaissance Orbiter Camera, or LROC, has captured millions of high-resolution images that display the textures of the highland soil, called regolith, in exquisite detail. These images show that the surface is not simple, unbroken bedrock. Rather, it is mostly made up of breccias, rocks formed from angular fragments of older rocks that have been fused together by the extreme heat and pressures of countless impacts. This tells us that the highland terrain has been shattered, churned, and compacted over billions of years, a continuous record of cosmic collisions. The scientific importance of the lunar highlands cannot be overstated. They act as a kind of Rosetta Stone for understanding both the Moon's formation and the early history of our solar system. For one, the highlands provide strong support for the lunar magma ocean hypothesis. Their widespread composition of anorthosite, a light-coloured rock, suggests that the Moon began as a mostly molten body. As it cooled, the lighter anorthositic material floated to the surface, forming the early crust. By studying the exact composition and layering of the highlands, scientists can refine models of how the Moon differentiated as it solidified and how its internal heat evolved during its earlier stages. The highlands are also crucial for establishing the timeline of solar system events. Because they are so heavily cratered, they preserve the oldest and most continuous record of impacts, including those from the period known as the Late Heavy Bombardment. By counting craters in different highland regions and linking them to absolute ages measured from Apollo mission samples, scientists can construct a detailed chronology of lunar impacts. This method of crater counting can then be applied to other airless bodies, such as Mercury, or the ancient cratered terrains of Mars, where we do not yet have returned samples. In this way, the Moon's highlands serve as a key chronological framework for understanding how the inner planets evolved in their earlier stages. In addition, the lunar highlands offer a rare glimpse into early planetary evolution. Unlike Earth, whose ancient crust has mostly been erased and recycled by tectonic activity, volcanic eruptions and erosion, the Moon's highlands have remained largely intact for billions of years. This makes them a kind of fossil record, preserving the surfaces of rocky planets as they might have looked in their infancy. Studying these ancient terrains allows scientists to learn how terrestrial planets formed their crusts, how they were reshaped by massive impacts, and how the early solar system operated during its first few 100 million years. While the highlands are not generally rich in easily accessible volatiles like water ice, their ancient and unique composition may still hold other valuable resources, potentially linked to the very processes that created them. From an exploration standpoint, untouched highland regions, especially on the Moon's far side, are highly attractive targets for future sample return missions. Bringing back pristine samples of the oldest lunar material could answer fundamental questions about the Moon's original composition, the timing of key early solar system events, and the processes that built its crust. These samples would complement the wealth of data collected by orbiters, giving scientists a ground truth to confirm and refine remote sensing observations. The study of the lunar highlands, led by NASA and other space agencies, has transformed our perception of the Moon. Once thought to be a static, unchanging orb, the Moon is now recognized as a dynamic body with a rich and complex history. From the first blurry photographs to the precise measurements and detailed mapping of modern orbiters, combined with direct Apollo sample analysis, every mission has added layers of understanding. The highlands are not just rugged ancient landscapes, they are natural laboratories, offering priceless insights into the Moon's fiery birth, its global differentiation, and the chaotic early days of the solar system. They continue to reveal secrets about the formation of rocky planets and the processes that shaped our cosmic neighborhood in its earliest chapters. For generations, the Moon has grown and shrunk through its monthly cycle. Yet, even though it seems close and well known, a persistent misunderstanding about our space neighbor has taken hold in popular culture and everyday language. The idea that there is a dark side of the Moon, a side that is always in shadow and never sees the sun. This idea is completely wrong, coming from a mix-up between a side being hidden from Earth and a side being hidden from sunlight. Through many years of careful watching and exploring by NASA missions, this myth has been fully proven false. The truth, backed by strong scientific evidence, is that the whole Moon, both the side we can see from Earth and the side we cannot, goes through a regular cycle of day and night just like our own planet. The reason people have this widespread misunderstanding comes from the Moon's special way of moving with Earth, called tidal locking. The Moon is tidally locked to Earth, which means that the time it takes to spin once on its own axis is exactly the same as the time it takes to go all the way around Earth. In simple terms, the Moon takes the same amount of time to turn once on itself as it does to make one full orbit around Earth. This synchronized motion makes sure that the same side of the Moon always faces our planet. This is why we always see the same patterns of craters and dark plains, called Maria, when we look at the full Moon. The side of the Moon that always faces Earth is called the near side, while the side that always faces away from Earth is called the far side. Because we always see the same face, people often wrongly think the far side must always be dark. But in this case, dark just means without sunlight. Sunlight comes from the sun, not the Earth. The Moon moves around Earth, and both Earth and the Moon move around the sun. As the Moon travels around Earth, the sun lights up different parts of its surface. Like Earth, the Moon has a line called the terminator, which is the boundary between the sunlit day side and the shadowed night side. This line moves across the Moon's surface as it spins and orbits the sun. Imagine a person walking around a big circle, always keeping their face pointed toward the center. As they walk, their back would always point outwards, away from the center. But the sun could still shine on their back while they move. In the same way, the Moon's back, its far side, always faces away from Earth, but it is not always facing away from the sun. As the moon goes around Earth, sunlight reaches its whole surface. Let us look at the moon's day and night cycle. A full lunar day, which is the time it takes for the sun to appear to move once across the moon's sky and return to the same spot, is about 29.5 Earth days long. This period is often called a synodic month. During this almost 30-day cycle, every part of the moon's surface gets about 14 Earth days of sunlight, followed by about 14 Earth days of darkness. This includes the far side. When the near side is in its full night, the far side is fully lit by the sun, enjoying its lunar day. And when the near side is fully lit, as during a full moon seen from Earth, the far side is in complete darkness, having its lunar night. Think about the moon's phases as we see them from Earth. When there is a new moon, the moon looks dark because the side facing Earth is not lit by the sun. At that time, the whole far side is bathed in sunlight. It is having its lunar day. When there is a full moon, the near side is fully lit by the sun, and at that exact moment the far side is completely dark, having its lunar night. As the moon moves through its phases from new moon to full moon and back again, the line of sunlight, the terminator, moves steadily across both sides. So over a lunar month, both sides get roughly equal sunlight. There is no side that is always dark. This myth probably comes from the phrase dark side, which in English can mean hidden or unknown, not necessarily without light. Before space exploration, the far side was dark in the sense that no human had seen it. It was a blank space on lunar maps, a place full of guesses. This unclear use of language caused confusion, but with the start of space exploration, people could directly see and photograph the far side, completely clearing up this mistake. NASA played a key role in confirming that the far side gets sunlight. The first mission to photograph the far side was the Soviet Luna 3 in October of 1959. Even though its pictures were blurry, they were taken when the far side was lit by the sun, otherwise no images would have been possible. These first pictures already showed sunlight on the far side, but it was NASA's Apollo program, especially Apollo 8 in December of 1968, that gave the first direct human proof that the far side gets sunlight. As the Apollo 8 crew, Frank Borman, James Lovell and William Anders, orbit the moon, they were the first humans to see the far side up close. Their live television broadcast to Earth, although a little grainy, showed the far side lit by the sun as they came from behind the moon. Astronaut William Anders took the famous Earthrise photograph during Apollo 8. This photo from lunar orbit shows a crescent Earth rising above the rocky sunlit moon. The moon's surface in the front of this picture is clearly lit by the sun, showing that the far side gets daylight. The astronauts also described the far side as sunlit but full of craters. Their reports made it very clear that the far side gets periods of full sunlight. Later Apollo missions supported this understanding. Every Apollo mission to the moon, from Apollo 8 to Apollo 17, included many orbits, passing over the far side. During these passes, astronauts watched and recorded the far side, often using high-resolution cameras in the command and service modules. These cameras took thousands of pictures of the far side in different lighting, clearly showing it fully lit by the sun during its lunar day. The photographic evidence from these missions is huge and undeniable, showing the moving terminator and the full sunlight on the far side when it faces the sun. Beyond the famous Apollo missions, NASA has sent a series of robotic explorers that have revealed even more about the moon, with astonishing detail and precision. In the 1960s, the Lunar Orbiter program systematically photographed nearly every part of the moon, including the mysterious far side, using high-resolution cameras. These orbiters produced extensive photographic atlases, showing the far side under many different lighting conditions, even fully bathed in sunlight. These early images were vital for scientists trying to understand the moon's surface and geological features, and they also proved something very important. The far side of the moon does in fact receive sunlight just like the side we see from Earth. In more recent times, NASA launched the Lunar Reconnaissance Orbiter, often called LRO, in 2009. Since then, it has circled the moon continuously, gathering an enormous amount of data that far surpasses anything collected before. LRO's main camera, known as the Lunar Reconnaissance Orbiter Camera or LROC, has taken millions of sharp, detailed images covering the entire lunar surface, including every corner of the far side. These photographs are taken under a variety of sunlight conditions, from the high sun that flattens shadows to the low sun that casts long, dramatic shadows across craters and mountains. All of these images are available for anyone to see, and they clearly show the far side glowing under the sun during its daytime. Many LRO maps even display both sides of the moon at once, with the moving line of day and night, the terminator, sweeping across the surface, offering clear visual proof that the far side experiences sunlight just like the near side. LRO carries other instruments that provide indirect evidence of sunlight too. One of these is the Diviner Lunar Radiometer experiment, which measures the temperature of the moon's surface. Data from Diviner reveal dramatic swings in temperature on the far side. During lunar daytime, the surface can soar to hundreds of degrees above 0 Fahrenheit, while at night it plunges to hundreds of degrees below 0 Fahrenheit. These extreme changes happen because the surface is heated directly by the sun and then cools rapidly when the sun sets. Exactly what you would expect for a region that experiences both day and night. If the far side were always dark, its temperatures would remain consistently freezing, like the permanently shadowed craters near the moon's poles which never see sunlight. One reason the myth of the dark side persists is that it confuses two very different ideas: the side of the moon that is always hidden from Earth and the side that is always dark. These are not the same. The far side is indeed hidden from our view, meaning we can never see it directly from Earth. But it is not in eternal darkness. It has its own cycle of day and night, just like the near side. The only truly permanently dark areas on the moon are found in certain deep craters near the lunar poles. These areas are called permanently shadowed regions because the crater floors are so deep and the rims so high that sunlight never reaches them, no matter the time of a lunar day or night. These permanently dark pockets are rare and isolated, while the vast majority of the far side is regularly illuminated by the sun, enjoying its own cycle of days and nights. For much of the 20th century, scientists thought of the moon as a completely dry, geologically inactive world, with no water at all. Samples brought back by the Apollo missions in the 1960s and 1970s seemed to support this idea, because they showed almost no evidence of water. This view had a strong influence on early plans for exploring the moon, suggesting that any humans living there in the future would have to bring all their water from Earth, which would be expensive and difficult to manage. However, over the last few decades, our understanding of water on the moon has changed dramatically, thanks to a series of advanced robotic missions, many led by NASA. This new understanding has turned the moon in our minds from a dry desert into a body that could hold valuable resources, with important consequences for future human exploration and the long-term sustainability of lunar bases. Searching for water ice in the moon's permanently dark craters has become a central part of modern lunar science and exploration plans. The search for lunar water ice picked up speed in the 1990s. The first strong clue came from NASA's Clementine mission, launched in 1994. Clementine, an orbiting spacecraft, carried a special radar experiment. This experiment sent radio signals from the spacecraft to the moon's polar regions, and then detected the signals that bounced back to Earth. The way the reflected signals behaved, especially in a property called circular polarization ratio, showed unusual patterns in some permanently dark craters near the moon's south pole. These patterns were consistent with the presence of water ice. While not a full confirmation, Clementine's data gave strong indirect evidence that ice might be in these very cold areas. It sparked renewed scientific interest and focused future missions on the moon's poles. After Clementine's hints, NASA sent the Lunar Prospector mission in 1998. Lunar Prospector carried a neutron spectrometer, a very sensitive tool that could detect hydrogen atoms. When cosmic rays hit the moon's surface, they produce neutrons. If these neutrons hit hydrogen atoms, they slow down. The neutron spectrometer measured a significant slowdown of neutrons coming from the moon's polar regions, especially inside permanently shadowed craters at both the north and south poles. This showed a higher concentration of hydrogen. Because these areas are extremely cold, the most likely explanation for the extra hydrogen was water ice, in the form of H2O molecules. The neutron spectrometer could not definitively tell the difference between water ice and other types of hydrogen, such as hydrogen in rocks or hydrocarbons. However, the strong link to permanently dark areas made water ice the leading possibility. This mission provided much stronger evidence, moving the idea of lunar ice from speculation to strong probability. Water ice can survive on the Moon because of the special conditions at the poles. The Moon's axis is tilted only about 1.54 degrees relative to its orbit around the Sun. This tiny tilt means the Sun stays very low on the horizon at the poles. As a result, some deep craters near the poles have floors and walls that never see direct sunlight. These areas are called permanently shadowed regions, or PSRs. Without sunlight, temperatures in these PSRs drop to extreme lows, reaching as cold as -396 degrees Fahrenheit, or about -243 degrees Celsius. At these freezing temperatures, water ice, if it arrives on the Moon, can stay stable for billions of years, resisting evaporation into space. These areas act like cold traps, preserving any water molecules that enter them. The water is thought to come mainly from comets and asteroids that have hit the Moon over time. These objects often contain large amounts of water ice. When they strike the Moon, some of the water vapor can move across the surface and collect in the cold traps, where it freezes. In addition, the solar wind, a stream of charged particles from the Sun, can implant hydrogen into the Moon's surface. This hydrogen can combine with oxygen from lunar minerals to form hydroxyl, and sometimes small amounts of water. Some of this water can also move to the cold traps. The first definite proof of water ice came from NASA's Lunar Crater Observation and Sensing Satellite, or LCROSS, in 2009. LCROSS was a bold mission designed to detect water directly. It had two parts: a used Centaur rocket stage and a shepherding spacecraft. In October of 2009, the Centaur rocket was intentionally crashed into Cabeus crater, a large, permanently dark crater near the Moon's south pole. The impact created a plume of debris that rose above the crater. Immediately after the impact, the shepherding spacecraft flew through the plume, analyzing it with instruments, including a visible light spectrometer, a near-infrared spectrometer, and a mid-infrared camera. The LCROSS data was clear. The instruments directly detected strong signs of water vapor and water ice in the plume. They also found other volatile materials like hydroxyl, carbon monoxide, carbon dioxide, sodium and silver, showing that the lunar polar soil is more complex than previously thought. This direct detection confirmed that water ice really exists in the Moon's permanently dark regions. It was a groundbreaking discovery, changing our understanding of lunar water from assumption to fact. LCROSS's findings reshaped how scientists view the Moon's water cycle and its potential as a resource. At the same time, NASA's Lunar Reconnaissance Orbiter, or LRO, also launched in 2009, has continued to provide detailed data on water ice and permanently shadowed regions. LRO's lunar orbiter. Laser Altimeter, or LOLA, has made very precise three-dimensional maps of the lunar poles, identifying and describing thousands of permanently dark craters and depressions. These maps help scientists find which areas never see sunlight and are likely to hold ice. LRO's Diviner Lunar Radiometer experiment measures surface temperatures and has confirmed that these PSRs are cold enough to keep water ice. LRO's Lunar Reconnaissance Orbiter camera, or LROC, has taken high-resolution images of these regions, using faint Earth light to sometimes illuminate the shadows, giving visual context for the other instruments' findings. While LROC cannot directly see the ice in darkness, its images help understand the environment where the ice exists. The form and spread of the water ice are still being studied. Evidence suggests the ice is not in thick, pure sheets like glaciers on Earth. Instead, it is mixed with lunar soil and broken rock called regolith. The ice content varies, estimated between a few percent and up to 20% by weight in some PSR areas. This means future extraction would likely involve heating the regolith to release water vapor, which could then be collected. The total amount of water ice in the polar cold traps is still being estimated, but current models suggest hundreds of millions of tons could exist across both poles, though more data will refine this number. The confirmed presence of water ice on the Moon has big implications for future space missions and long-term lunar exploration. Water is extremely valuable. First, it is essential for human life. Having water on the Moon would reduce the need to bring it from Earth, making long-term missions and lunar bases more practical and cheaper. Astronauts could use it for drinking, hygiene, and growing food. Second, water can be split into hydrogen and oxygen through electrolysis. Both are strong rocket fuels, and oxygen is also needed for breathing. If water ice can be mined and processed into fuel on the Moon, it could become a space gas station, refueling missions to places like Mars. This would greatly reduce the cost and difficulty of deep space travel, since rockets would not need to carry all their fuel from Earth. The idea of using resources where they are found, or in situ resource utilization, ESRU, is central to NASA's future plans, and lunar water ice is a key target. NASA is planning more missions to study and use lunar water ice. The Artemis program, NASA's project to return humans to the Moon, focuses on the South Pole because of the confirmed ice. Future robotic landers and rovers are being designed to operate in these extreme cold traps to survey the ice, check its purity, and test extraction methods. These missions will help us understand the ice's exact nature and location, guiding the design of future lunar bases and water extraction systems. The ultimate goal is to build a lasting human presence on the Moon, and access to water ice is considered essential for achieving this vision. The search for water ice on the Moon tells a story of how our understanding of the universe keeps changing. For a long time, the Moon was thought to be a dry, lifeless and empty world, completely lacking water or other resources. Yet, over the years, it has slowly revealed a surprising secret. It is not just a barren rock, but a place that holds valuable materials that could support future space missions. This discovery has challenged old ideas and opened up exciting new possibilities for humans to explore. The determined and creative work of NASA, together with its international partners, using highly advanced instruments and clever mission plans, has completely changed what we know about water on the Moon. Their discoveries have paved the way for a new chapter in space exploration, not only on the Moon but also far beyond into deep space. Even the Moon's permanently shadowed regions, areas that were once thought to be endlessly cold, dark and lifeless, are now seen in a new light. These hidden corners may hold essential water ice, offering a potential supply for astronauts and future settlements, turning once overlooked places into possible starting points for humanity's next giant steps among the stars. The Moon exerts a gentle but persistent gravitational pull that not only keeps it moving in its steady orbit around Earth, but also subtly affects the paths of spacecraft that venture near it. Gravity, at its heart, is a simple concept. It is the invisible force that pulls any two objects with mass toward each other. Yet, when we look at the Moon, this pull is far from uniform. Its gravitational field is not a smooth, perfectly even blanket of force. Instead, it contains small but measurable variations, which scientists call gravity anomalies. These anomalies arise from uneven distributions of mass within the Moon and on its surface. Regions where the Moon's crust or interior contains slightly more mass exert a stronger pull, producing what is called a positive gravity anomaly. Conversely, areas with less mass than expected produce weaker gravitational effects, creating negative anomalies. Over the decades, NASA's robotic probes have been crucial in detecting and mapping these variations, particularly on the far side of the Moon, offering remarkable insight into the Moon's inner structure and its long and complex geological history. The first hints of these strange gravitational patterns were discovered almost by accident in the 1960s during the earliest lunar orbital missions. As NASA's lunar orbiter probes circled the Moon, and later as the Apollo command and service modules prepared for human landings, mission controllers noticed that the spacecraft were not following perfectly predictable paths. They would sometimes speed up or slow down ever so slightly, subtly shifting their orbits. These deviations were not random. Instead, they repeatedly occurred over specific areas of the Moon's surface, posing an unexpected challenge for navigation. Controllers had to make careful and frequent corrections to keep the spacecraft on their planned trajectories. Scientists soon realized that these orbital quirks were not due to mistakes in navigation, but rather to real, localized differences in the Moon's gravitational pull. The areas of unexpectedly strong attraction were eventually given the nickname mascons, short for mass concentrations. The first mascons were mostly linked to the Moon's large circular mare basins on the near side. These basins, such as Mare Imbrium or Mare Serenitatis, are vast, dark plains formed by ancient volcanic lava flows lying lower than the surrounding highlands. The revelation that these low-lying regions contained hidden concentrations of mass beneath them was a surprising puzzle, overturning earlier assumptions that the Moon's interior was largely uniform. To map these gravitational anomalies with greater accuracy, NASA developed increasingly sophisticated tracking techniques. In the early days, this involved carefully monitoring radio signals sent from the spacecraft back to Earth. Tiny changes in the frequency of the radio waves, a phenomenon known as the Doppler effect, revealed subtle shifts in the spacecraft's speed. A slight increase in frequency meant the spacecraft was being pulled a little faster by stronger gravity, while a decrease indicated it was slowing down over a region with weaker gravity. This method was very effective for initial detection, but only produced a rough picture of the Moon's gravitational landscape. Over the following decades, dedicated gravity mapping missions dramatically improved our understanding. The lunar orbiter missions in the 1960s provided the first detailed, though imperfect, maps of the nearside mascons. Later, data from the Apollo command and service modules, particularly those from missions carrying scientific instruments, offered sharper measurements. In the 1990s, missions such as Clementine in 1994 and Lunar Prospector in 1998 refined these maps further. Lunar Prospector, in particular, produced the first truly global gravity maps of the Moon, extending coverage to the far side, although some details remained limited. The greatest leap in lunar gravity mapping came with NASA's Gravity Recovery and Interior Laboratory mission, better known by its acronym GRAIL. Launched in 2011, GRAIL consisted of two identical spacecraft, nicknamed Ebb and Flow, flying in close tandem around the Moon. The concept behind GRAIL was beautifully simple. As the two spacecraft passed over areas with different gravitational strengths, tiny changes in their relative distance would occur. Flying over a positive gravity anomaly caused the leading spacecraft to speed up slightly, temporarily increasing the gap, followed by the trailing spacecraft accelerating in turn and closing the gap. Flying over a negative anomaly produced the opposite effect. By measuring these minuscule changes in distance with micrometer-level precision, GRAIL was able to create the most detailed and accurate global gravity map of the Moon ever produced. This map offered unprecedented insight into the far side, revealing features and structures that had been invisible or poorly understood before, and deepening our understanding of the Moon's hidden interior. The discoveries made by NASA's lunar missions, especially the twin GRAIL spacecraft, have opened an extraordinary window into the Moon's hidden interior and its long, dramatic geological history. One of the most remarkable revelations concerns the mysterious mascons, or mass concentrations, found on the near side of the Moon. Scientists now understand that these strong gravity highs are largely caused by the dense, dark basaltic lava that flooded enormous impact basins to form the familiar lunar Maria, the smooth, shadowy plains visible even from Earth. The events that created these vast basins were unimaginably violent. When massive asteroids or comets struck the Moon, they blasted away huge amounts of crustal rock and left the lunar crust significantly thinner in those regions. In the aftermath, molten rock from deep within the Moon welled up through the weakened crust, slowly filling the basins with dense basalt. This lava is much heavier than the lighter anorthosite rocks that make up most of the Moon's highlands. The result of this combination, thick, heavy lava plains and in some areas, a slight rise of the denser mantle beneath, produced the excess mass that we now measure as mascons. These mascons also tell a fascinating story about the Moon's rigidity. On Earth, if a mass imbalance like this formed, the planet's crust and mantle would gradually shift and settle over millions of years, a process called isostatic adjustment, until the gravity balanced out. On the Moon, however, the large mascons have persisted for billions of years. This shows that the Moon's outer shell, its lithosphere, has been unusually stiff and resistant to change for nearly its entire history. In other words, after the Moon formed, its interior cooled and hardened relatively quickly, freezing the mascons in place. Unlike Earth, where the constantly moving and flowing interior erases such features over time, the Moon's solid outer layer preserves them almost perfectly. If we shift our gaze to the Moon's far side, a very different picture emerges. The far side lacks the dramatic positive mascons found on the near side. This makes sense because the far side is largely missing the huge, lava-filled basins that dominate the near side. With a thicker crust and less volcanic activity, magma could not erupt in the volumes necessary to create these massive gravity anomalies. Even the colossal South Pole Aitken Basin, the largest and deepest known impact basin on the Moon, and one of the biggest in the entire solar system, does not display a strong positive mascon like the Maria on the near side. While Grail's data shows a complex gravity pattern there, the signal is often subtle, or even slightly negative in the basin's deepest regions. This tells us that although the impact was enormous, excavating vast quantities of crustal material, the resulting mass deficit was not fully offset by mantle uplift or by dense lava filling. South Pole Aitken's gravity fingerprint reinforces the idea that the far side's crust is thicker, and that its volcanic and thermal history was very different from the near side's. Beyond these large basins, Grail's incredibly detailed gravity maps revealed countless smaller anomalies scattered across the entire Moon. These often correspond to individual craters, buried structures, or tectonic features. For example, the central peaks of large craters, pushed upward by the impact, create small gravity highs, while the hollowed-out crater floors can produce slight gravity lows. These tiny variations provide an unprecedented glimpse beneath the surface, exposing hidden rifts, fractures, or even concealed lava tubes invisible to ordinary imaging. Essentially, Grail allowed scientists to X-ray the Moon, revealing its inner architecture in 3 dimensions. The broader implications of these findings are profound. The persistence of near-side mascons and the discovery of numerous smaller anomalies across both hemispheres confirm that the Moon's lithosphere has remained rigid for billions of years. This rigidity tells us that the Moon cooled quickly after its formation and became geologically inactive much earlier than Earth, with no plate tectonics to erase these long-lived features. The precise gravity measurements also offer vital clues about the Moon's structure. When combined with surface height data from missions like the Lunar Reconnaissance Orbiter's laser altimeter, scientists can map crustal thickness in exquisite detail. These models show that the far side has a thicker crust, while the near side beneath the Maria has thinned crust. Gravity data also helps reveal the depth and density of the mantle, and even the Moon's small core, giving a full 3-dimensional picture of its internal structure. However, the contrast between the near and far sides highlight a deep asymmetry in the Moon's interior. This asymmetry, extending far below the surface, reflects the uneven processes that shaped the Moon in its earliest days, from the giant impact that formed it to the subsequent cooling and volcanic activity. Even the way the Moon's interior responded to colossal impacts, as revealed by gravity, provides crucial insights into the physics of such events, including how crust and mantle react to enormous collisions. Grail's meticulous gravity mapping has unveiled a Moon that is both rigid and complex, revealing its hidden depths, its ancient violent history, and the subtle differences between its 2 hemispheres. The Moon's intricate gravitational patterns continue to tell the story of a world that has preserved its deep secrets for billions of years, offering scientists an extraordinary glimpse into its inner life. The Moon, as we see it today, does not have a global magnetic field like Earth's. Earth's strong magnetic field comes from a moving dynamo inside its molten, swirling metal outer core, which works like a giant electric generator. For many years, scientists thought the Moon's interior was mostly cold and inactive, too small and too cool to support such a process. However, a series of discoveries from NASA missions, especially those studying the far side, have shown surprising evidence that challenges this long-held idea. These findings point to the presence of weak, local magnetic fields trapped in the Moon's crustal rocks. These fossil magnetic fields, leftovers from a long ago time, give important clues about whether the Moon once had an active, Earth-like core that created a strong global magnetic field in its distant past. The first direct proof of lunar magnetism came from the Apollo missions in the 1960s and 1970s. During the Apollo 12, 15, and 16 missions, astronauts placed magnetometers directly on the Moon's surface. These tools detected very weak, but measurable magnetic fields stored in the lunar rocks at the landing sites. At the same time, magnetometers aboard the Apollo command and service modules, which orbited the Moon, also detected these local magnetic anomalies from above. These early discoveries were surprising because a small, seemingly dead in geological terms body like the Moon was not expected to have any noticeable magnetic field. The fields found were not active global fields, but remnant magnetism, meaning the rocks had picked up a magnetic signature at some point in their past and kept it. The full extent and pattern of these crustal magnetic anomalies became clearer with later NASA robotic missions. The Lunar Prospector mission, launched in 1998, carried a special magnetometer that created the first global maps of these weak local magnetic fields. Lunar Prospector's data showed that these crustal magnetic anomalies are spread across the Moon's surface, but they are stronger and more common on the far side. This uneven pattern of magnetic fields became a major scientific puzzle and an important area of study. In particular, some of the strongest magnetic anomalies on the far side were found to be located directly opposite some of the Moon's largest and youngest impact basins on the near side. The fact that these strong remnant magnetic fields exist in lunar rocks suggests an important point. These rocks gained their magnetism when the Moon did have a global magnetic field, created by an internal dynamo. The strength of some of these ancient magnetic fields is too large to have been caused by outside sources, like temporary effects from the solar wind. They strongly suggest that a powerful internal dynamo, similar to the one that makes Earth's magnetic field, was working in the Moon's core billions of years ago. This discovery changed how scientists understand the Moon's early development, showing it was not just a cold, inactive body, but may have once had a lively, active interior. For a planet or moon to create a global magnetic field through a dynamo, certain conditions must be met. It needs a core that is at least partly molten and can conduct electricity, moving because of heat differences and spinning fast enough. In the Moon's early history, scientific models now suggest that its small metal core was indeed hotter and more molten than it is today. The source of energy that drove this movement in the core is still being studied, but several ideas exist. One is heat convection, where the core's internal heat or its cooling makes the molten material move. Another is compositional convection, where lighter elements separate from heavier ones inside the molten core, causing movement. A third idea involves mechanical stirring, possibly caused by strong tides from Earth or by a slow wobble of the Moon's axis in its early, perhaps closer orbit. Whatever the exact cause, the magnetic evidence shows that these conditions existed in the early Moon. The timing of this ancient lunar dynamo is also learned from the magnetic clues. The strongest magnetic anomalies are in crustal rocks that formed relatively early in lunar history, about 4.2 billion to 3.2 billion years ago. The lack of strong magnetism in younger lunar rocks suggests that the lunar dynamo, after running for around a billion years, quickly weakened or stopped entirely. This shutdown left the Moon without a global magnetic shield, making its surface more exposed to the solar wind and cosmic radiation, which may explain why it has almost no atmosphere today. The dynamo likely stopped because the Moon's small core cooled and solidified quickly, or because the forces driving the movement weakened. The concentration of stronger magnetic anomalies on the far side, especially those directly opposite large, young impact basins on the near side, gives a strong hint about how they formed. This is explained by the impact or antipodal focusing hypothesis. According to this idea, the huge, powerful impacts that created the large basins on the Moon's near side, like Mare Imbrium or Oriental Basin, sent strong seismic waves through the Moon's interior. When these waves met and focused on the opposite side of the Moon, the antipode, they could have heavily shocked, cracked and heated the crustal rocks there. This seismic energy might have caused local melting, recrystallization, or physical changes in the rocks. As the rocks cooled or reorganized in the presence of the Moon's early active global magnetic field, they gained and held a strong remnant magnetization. In short, the impact energy helped the local crust capture a permanent magnetic signature from the global field. Since many antipodes of the largest near-side basins are on the far side, this explains why magnetic anomalies are stronger and more common there. Adding to the fascination of lunar magnetism are features called magnetic swirls or lunar swirls. These are unusual, light-coloured swirling patterns seen on the Moon's surface. They are usually irregular, bright, curving, and often look like someone drew on the Moon with a light-coloured pencil. These swirls do not match any clear topographic features, like hills, valleys, or craters, which makes them unique. Many of these swirls, including the most famous one, Rhina Gamma on the near side, are always found where strong local magnetic anomalies exist. The main idea for their formation is that these magnetic fields act as small shields, deflecting charged particles from the solar wind, which normally darken the moon's surface over time. By protecting the surface, the rocks remain brighter and less weathered. While Reiner Gamma is on the near side, similar though often smaller, swirls are found on the far side, also matching the locations of magnetic anomalies. These swirls are clear, visible proof of how crustal magnetism affects the lunar surface. The magnetic clues tell us a lot about the moon's interior and its history. First, finding evidence of a past lunar dynamo changes how we understand how planetary cores work. It shows that even small celestial bodies, once thought too small to have a dynamo, can create a strong global magnetic field for a long time in their early history. This changes how we think planetary cores form and cool. It suggests that the moon's core was more active and dynamic in the distant past than previously thought, pointing to a more complex history of internal heat and movement that drove the dynamo. Secondly, studying the moon's ancient magnetic field gives scientists a window into its long-lost thermal past. The very existence of a dynamo, a natural magnetic generator deep within the moon, suggests that billions of years ago the moon's interior was much hotter than it is today. Its core must have been molten and active, capable of producing a magnetic field that stretched across the whole moon. Over time, as this internal engine slowed and finally stopped, it marked a period when the moon's core cooled quickly and solidified. By examining these changes, scientists can estimate how fast the moon lost its internal heat and understand how its inner layers gradually evolved over billions of years. Thirdly, the way magnetism is distributed across the lunar crust offers important clues about how planetary surfaces gain and preserve magnetic properties. One fascinating idea is that some magnetic anomalies on the far side of the moon may be connected to massive impacts on the near side. This shows how events occurring on one part of a planet can produce far-reaching effects, altering both the surface and its magnetic character. The magnetic patterns we observe today are not random scribbles. They are like fingerprints, telling a story of powerful cosmic collisions, global interactions, and long, slow thermal evolution. Fourthly, a global magnetic field in the moon's early history would have acted as a shield, offering some protection from the harshness of space. It would have helped deflect energetic particles from the solar wind and cosmic rays, much like Earth's magnetic field does today. Once this protective field disappeared, the moon's surface, and any thin early atmosphere it may have had, became directly exposed to these destructive forces. Understanding this shift is crucial for scientists trying to reconstruct how the lunar surface changed over billions of years and how it interacted with the surrounding space environment. Finally, the uneven distribution of magnetic anomalies strongly highlights the deep differences between the moon's near side and far side. These differences are not only visible in surface features or variations in crust thickness. They run deep into the moon's internal structure and influence how it responded to large-scale cosmic events. NASA has been mapping and studying these faint localized magnetic fields using instruments aboard missions like Lunar Prospector and by analyzing data from international missions such as the Japanese Kaguya-Selene mission. These efforts continue to sharpen our understanding, and future missions may carry even more sensitive magnetometers to create higher resolution maps. Such studies will reveal precisely how the moon's magnetic fields interact with the solar wind, gradually uncovering the hidden, dynamic history written in the moon's ancient magnetism. At first glance, the moon's surface may appear smooth and uniform when we gaze at it from Earth. Yet, a closer look reveals a far more intricate and fascinating picture, a patchwork of many different types of rocks and minerals, each with its own story to tell. Understanding the moon's rocks and minerals is essential for unraveling the secrets of its birth, its long journey through time, and the hidden structure beneath its surface. Simply put, rocks are solid, natural mixtures made up of one or more minerals, while minerals themselves are solid chemical substances that form naturally with a precise crystal arrangement. Most of the moon's rocks are igneous, meaning they were created when molten rock cooled and hardened. But the moon's surface also contains large amounts of breccias, rocks made from fragments of older rocks smashed together and glued by the intense heat and pressure of impacts. NASA's thorough lunar missions, from astronauts bringing back rock samples to sophisticated instruments on orbiting spacecraft, have carefully mapped and identified these rocks and minerals. These efforts have allowed scientists to compare the familiar near side of the moon with the mysterious far side, revealing an astonishing variety of geological features and giving deep insight into the Moon's history and internal structure. Among the Moon's minerals, the most common and widespread is plagioclase feldspar, which forms the main part of a rock called anorthosite. Anorthosite is a light-coloured, relatively low-density igneous rock that dominates the Moon's bright, rugged highlands. Scientists believe that anorthosite formed very early in the Moon's history, around 4.5 billion years ago, when the Moon was enveloped by a vast global ocean of molten rock, known as the lunar magma ocean. As this ocean slowly cooled, the lighter minerals, including plagioclase feldspar, floated to the surface. Layer by layer, they built up what became the Moon's first crust, the highlands we can still see today. The widespread presence of anorthosite, especially on the far side of the Moon, stands as strong evidence of this early separation into distinct layers, a dense core, a mantle, and a lighter crust. In contrast, the Moon's darker, smoother plains, called maria, are made mostly of a very different rock, basalt. Lunar basalts are dark, fine-grained rocks rich in iron and magnesium-bearing minerals such as pyroxene and olivine, and often containing substantial amounts of titanium. These basalts formed from volcanic activity, when molten lava poured into large impact basins and solidified. The presence of pyroxene and olivine is particularly interesting because these minerals also exist in the Moon's mantle beneath the crust, showing that the lava of the maria came from partially melted material deep inside the Moon. Another special and scientifically important rock type is curipe, an acronym for potassium, rare earth elements, and phosphorus. These elements are called incompatible because they do not easily fit into the crystal structure of common rock-forming minerals like plagioclase feldspar or pyroxene. As the lunar magma ocean solidified, these incompatible elements became concentrated in the last remaining molten pockets. When these creep-rich melts erupted, they produced creep basalts, which are often rich in radioactive isotopes that generate internal heat. The uneven distribution of creep rocks provides crucial clues about the Moon's volcanic activity and its thermal evolution over billions of years. The Moon's surface is also dominated by breccias. For billions of years, asteroids and comets have bombarded the Moon, pulverizing its surface. As a result, the Moon is largely covered by a thick layer of regolith, a loose fragmented soil made up of dust, tiny rock pieces, and glass beads formed by impact melting. Buried within this regolith, and extending deeper into the crust, are countless breccias. These rocks are like natural concrete, fragments of older rocks smashed together and fused under the enormous pressures and heat of later impacts. Polymicted breccias, which contain fragments of many different rock types, are especially common in the highlands, showing just how much the lunar surface has been reshaped over time. The most direct way scientists have studied the Moon's rocks is by examining samples brought back by Apollo astronauts. Between 1969 and 1972, astronauts collected about 842 pounds, 382 kilograms, of lunar material, including rocks, soil, pebbles, and core samples, from 6 landing sites on the Moon's near side. These samples confirmed that anorthosite dominates the highlands, basalt forms the maria, and creep-rich rocks exist in specific regions. Careful laboratory studies of these precious materials revealed their exact chemical and isotopic makeup, helping scientists determine the Moon's age, how it separated into layers, and how it cooled over time. The Soviet lunar missions also returned small samples from 3 locations on the near side, further adding to our direct knowledge. But these physical samples come only from a few places on the Moon, mainly the near side. To study the rest of the Moon, especially the far side which astronauts have never visited, scientists rely on remote sensing instruments aboard orbiting spacecraft. These instruments do not bring rocks back to Earth. Instead, they analyze light, heat, or radiation reflected or emitted from the Moon's surface, allowing scientists to map its mineral composition and uncover its hidden geological secrets without ever touching the ground. One of the most important tools for discovering which elements make up the Moon's surface has been the gamma-ray spectrometer, often called the GRS. This instrument was carried on missions such as NASA's Lunar Prospector, which was launched in 1998. The GRS works in a fascinating way. When cosmic rays, high-energy particles from space, strike the Moon's surface, or when naturally radioactive elements like thorium, uranium, and potassium emit radiation, the GRS detects the resulting gamma rays. Each element produces gamma rays at very specific energy levels, like a unique fingerprint, allowing scientists to create global maps showing where different elements are most abundant. On the far side of the Moon, the GRS found far lower amounts of iron, titanium, and thorium compared to the large dark lava plains, or maria, on the near side. Because iron and titanium are common in volcanic rocks called basalts, this strongly suggested that the far side highlands are mostly made of anorthosite, a type of rock that is poor in these metals. The lower thorium levels also revealed that heat-producing materials, known as creep, are concentrated mainly on the near side. This difference helps explain why the two sides of the Moon have very different volcanic histories. Working alongside the gamma-ray spectrometer, Lunar Prospector also carried an X-ray spectrometer. This instrument detected X-rays bouncing off the lunar surface when it was illuminated by the sun. It was especially sensitive to lighter elements like aluminum, silicon, and magnesium. The X-ray data reinforced the picture of the far side highlands being mostly anorthosite, showing higher levels of aluminum, a key ingredient in plagioclase feldspar, and lower levels of iron, which matches what scientists expect from the Moon's original crust. Another remarkable tool aboard Lunar Prospector was the neutron spectrometer. Cosmic rays hitting the lunar surface produce neutrons, and when these neutrons pass through hydrogen atoms, they slow down. By detecting these slower neutrons, the instrument could locate hydrogen. The data showed elevated concentrations of hydrogen, interpreted as water ice, especially in permanently shadowed regions at the Moon's poles. Many of these icy, cold traps are on the far side, including the enormous South Pole Aitken Basin. This discovery was revolutionary, proving that the Moon holds a precious resource that scientists once thought did not exist. Earlier, NASA's Clementine mission, launched in 1994, carried a multispectral imager that photographed the Moon in many colours of light, from visible to near-infrared. Different minerals absorb and reflect light differently, producing unique spectral signatures. By studying these, Clementine helped create the first global maps showing the far side and near side highlands, dominated by anorthositic rocks. It also revealed signs of pyroxene and olivine, minerals usually found deep inside the Moon. These minerals were especially visible in large impact basins like the South Pole Aitken Basin, indicating that such massive collisions had punched through the crust and brought deep interior material to the surface. More recently, NASA's Lunar Reconnaissance Orbiter, or LRO, launched in 2009, has provided the most detailed compositional maps yet. LRO carries the Diviner Lunar Radiometer experiment, which measures heat, or thermal infrared radiation, from the surface. Different minerals release heat in distinct ways, creating a kind of thermal fingerprint. Diviner has used these fingerprints to produce detailed global maps of the Moon's main rock types, confirming the dominance of feldspathic, or anorthositic rocks in the highlands, and clearly showing the basaltic compositions of the maria. It can even distinguish between different kinds of silicate minerals, giving scientists a deeper understanding of the Moon's surface. While LRO's Lunar Reconnaissance Orbiter camera, or LROC, mainly takes high-resolution visible light pictures, these images are incredibly useful. They reveal the Moon's surface textures, the spread of boulders and rocks, and how worn down different features are. When combined with the spectral and elemental data, these pictures help scientists interpret the underlying rock types and the processes that shape them. For example, LROC images show that the highlands are often made up of brecciated rocks, smashed and reworked over billions of years by constant impacts. Some of the most exciting discoveries have come from the far side, particularly the vast South Pole Aitken Basin, which covers a huge portion of the far side. Data from orbital instruments suggest that this basin exposes rocks from deep within the Moon, including possible mantle material. Scientists have detected olivine and pyroxene, minerals usually buried in the Moon's interior, on the basin floor. This is incredibly important because it shows that the SPA impact was so powerful that it punched through the crust, exposing deep material without the need for drilling. It gives scientists a rare glimpse into the Moon's inner layers, revealing clues about its composition and formation. Although the far side of the Moon does not contain large fields of creep-rich basalts, scientists using orbiting instruments have discovered something intriguing. They have detected small and scattered spots with higher concentrations of thorium, which is one of the important elements found in creep. These patches are rare and limited in size, yet they tell an interesting story. Their presence suggests that the far side of the Moon may have experienced very localized volcanic activity, or perhaps unusual geological processes that somehow transported these heat-producing incompatible elements to the surface. Even though these exceptions are minor when compared to the larger patterns of lunar geology, they are extremely valuable because they help refine our picture of how heat once moved through the Moon's interior, and how the Moon cooled and changed over billions of years. The implications of these discoveries for lunar science are truly far-reaching. Thanks to the detailed maps created by NASA's orbiting instruments, scientists now have clear proof that the Moon is not symmetrical in its makeup. The crust on the far side is very different from the crust on the near side. The far side is dominated by bright anorthositic rocks and has a crust that is noticeably thicker, while the near side has thinner crust and larger basalt-filled plains. This strong contrast supports the idea of the lunar magma ocean, which proposes that soon after the Moon was born, its outer layers were once molten. As this molten ocean cooled, heavy materials sank inward and lighter minerals floated upward, creating the Moon's layered structure. Over time, this process gave rise to the different provinces we see today. The vast anorthositic highlands, the dark volcanic plains of the Maria, and scattered regions enriched in creep elements. Another important clue lies in what is missing. Unlike the near side, the far side does not show wide expanses of dark mare basalts. This absence is tied to its thicker anorthositic crust, which made it harder for magma to reach the surface, and also to the smaller amount of radioactive heat-producing elements that drive volcanic activity. This difference in composition shaped how much each hemisphere was resurfaced by lava. The detailed chemical maps from orbit also help scientists study impacts more closely. When asteroids and comets crash into the Moon, they dig up material from different depths, and by analysing this excavated matter, researchers gain a clearer idea of the Moon's inner layers. The far-side highlands, with their ancient and largely untouched anorthositic crust, act like a time capsule. They preserve evidence from the earliest moments of the Moon's history, including the first formation of its crust and the violent era of heavy bombardment that followed. Beyond their scientific value, these discoveries also have practical importance. The confirmed presence of water ice and the possibility of other useful minerals make the Moon a potential treasure house for future explorers. These resources could support human bases and provide raw materials for building and sustaining missions deeper into space. Every new wave of information collected by NASA's orbiters adds more pieces to this grand puzzle. Together, these data reveal that the Moon is not a simple, uniform body, but a world with two very different faces, each recording a different chapter of its long and complex geological story. When we gaze up at the Moon from Earth, its surface appears as a patchwork of two very different types of terrain. There are the bright, rugged highlands, pockmarked with countless craters from ancient impacts, and then there are the darker, smoother plains known as Maria, a Latin word meaning seas. Long ago, early astronomers imagined these dark patches were actual oceans of water, but modern science has revealed a very different story. These Maria are enormous plains of solidified basaltic lava, created by volcanic activity billions of years ago. On the Moon's near side, the side that always faces Earth, these dark lava plains cover roughly 30% of the hemisphere, giving it the familiar mottled, almost artistic look we all recognise. However, when we turn our attention to the Moon's far side, the hidden hemisphere that we cannot see from Earth, a striking geological mystery presents itself. Unlike the near side, the far side is overwhelmingly dominated by bright cratered highlands, with volcanic Maria covering barely 1% of the surface. This dramatic imbalance in volcanic activity between the two hemispheres has puzzled scientists for decades. Through decades of careful observation and exploration, NASA missions have provided some of the most compelling clues to explain why these dark volcanic plains are so rare on the far side. To understand this mystery, it helps to know how lunar Maria formed. These are not volcanoes in the classic cone-shaped form we see on Earth, such as Mount Fuji or Mauna Loa. Instead, they are enormous flood basalt plains, similar in scale to the colossal lava flows of the Columbia River Basalt Group in the United States or the Deccan Traps in India. The story begins with giant asteroid or comet impacts, which smashed into the Moon's surface and carved out enormous basins. Over the millions of years that followed, Molten lava from the moon's interior slowly rose through cracks and fractures in the thinned crust inside these basins. The lava spread across the basin floors and cooled, eventually forming the smooth, dark plains we now call Maria. Most of this volcanic activity occurred between 3,800,000,000 and 3,200,000,000 years ago, long after the moon's crust had first solidified. The near side boasts many magnificent examples such as Mare Imbrium, Mare Serenitatis, and Mare Crisium, each a silent witness to ancient, large-scale volcanic eruptions. The difference between the near and far sides becomes immediately clear when we compare high-resolution maps. The near side is patterned with large, dark maria that stand out against the brighter terrain, forming easily recognizable shapes and seas. The far side, by contrast, is a vast expanse of bright, ancient highlands, almost entirely lacking in these dark plains. The few maria that do exist on the far side are small, irregular, and confined to isolated basins, such as Mare Moscoviense and Mare Ingeni. This sharp contrast in volcanic resurfacing is one of the moon's most striking geological features and holds crucial clues about its evolution and internal structure. NASA scientists have proposed several explanations for the scarcity of maria on the far side. The most widely accepted theory revolves around a simple yet powerful idea. The thickness of the moon's crust is very different between the two hemispheres. Data from missions such as Lunar Prospector, Clementine, and especially the Gravity Recovery and Interior Laboratory, GRAIL, mission, have confirmed this difference with remarkable precision. The far side's crust averages about 60 kilometers, or roughly 37 miles in thickness, while the near side's crust is much thinner, averaging only about 30 kilometers, or roughly 18.5 miles. This variation in crustal thickness has a huge effect on the moon's volcanic activity. Magma, being lighter than the surrounding solid rock, naturally tries to rise toward the surface. But thick crust makes this journey far more difficult. On the near side, the thinner crust and the massive fractures created by impacts provided pathways for lava to flow to the surface, filling basins and creating extensive maria. On the far side, however, the thick crust acted as a formidable barrier. Even when huge impacts carved out massive basins, the magma beneath often could not break through in large enough quantities to form broad volcanic plains. Only occasionally did small eruptions occur in areas of unusual weakness, but these were too limited to reshape entire basins. As a result, the far side remains dominated by rugged cratered highlands, largely untouched by the volcanic resurfacing that gave the near side its characteristic dark seas. In this way, the moon's near and far sides tell two very different stories, one of ancient volcanic floods and vast, dark plains, and one of towering highlands scarred by countless impacts, quietly preserving the moon's earliest history. The contrast between them remains one of the most fascinating puzzles in planetary science, a silent reminder of the complex forces that shaped our closest celestial neighbour. A secondary, yet remarkably influential explanation for why the moon's far side has so few maria revolves around how heat-producing radioactive elements are unevenly spread throughout the moon's interior. Evidence for this comes largely from NASA's Lunar Prospector mission, which carried a sensitive gamma-ray spectrometer. This instrument revealed that certain radioactive elements, potassium, uranium, and thorium, which naturally release heat as they decay, are far more abundant on the moon's near side than on the far side. Scientists have named the region of concentrated radioactivity the Procellarum Creep Terrain, drawing its name from the vast Oceanus Procellarum on the near side and the creep-rich rocks found there. Because these heat-producing elements were concentrated on the near side, the underlying mantle there stayed warmer and partly molten for a much longer time. This lingering heat allowed magma to form more easily and rise through the relatively thinner crust, feeding volcanic eruptions that created the extensive maria we see today. On the far side, however, these radioactive elements are scarce. With less internal heat, the far side's mantle cooled more quickly, producing far less magma and sustaining much less volcanic activity. In other words, the moon's interior was not heated evenly. The near side became a hotspot for volcanic activity, while the far side remained comparatively frozen and quiet. Large impacts and basin formation also play a role in this story, but they do not provide the whole answer. While the near side has numerous large impact basins that were perfect containers for lava flows, the far side has massive basins too, including the enormous South Pole Aitken Basin, which is the largest and deepest known impact structure on the Moon. Yet, despite the presence of such vast depressions, the far side's thicker crust and cooler interior prevented extensive lava flooding. Even the South Pole Aitken Basin contains only scattered and small patches of mare. This shows that creating a giant impact basin alone was not enough to produce the wide, dark plains of lava. The crustal and thermal conditions beneath were equally important, if not more so. Some more advanced theories suggest that the Moon's early mantle might have had asymmetrical convection patterns or localized plumes of hot material that preferentially supplied magma to the near side. While direct evidence for these ancient mantle plumes is hard to obtain, data from NASA's Grail mission hints at variations in the Moon's internal density that could support such ideas. Tiny differences in the Moon's gravity across its surface reflect variations in mass within its interior, which may have been shaped by uneven heating and magma production. The Moon's formation and its tidal interactions with Earth might also have influenced these asymmetrical internal structures. NASA's multi-instrument approach has been key to unraveling this volcanic mystery. Visual mapping by missions such as the Lunar Orbiter program in the 1960s and the Lunar Reconnaissance Orbiter Camera, or LROC, which began in 2009, produced detailed photographs of the Moon's surface. These images clearly show the global distribution of Maria and confirm their extreme scarcity on the far side, allowing scientists to accurately measure the size and boundaries of these volcanic plains. Topographic measurements have been equally important. Missions like Clementine in 1994 and the Lunar Orbiter Laser Altimeter, or LOLA, aboard LRO, mapped the depths of impact basins and the heights of mare plains. These elevation maps revealed that Maria almost always occupy low-lying basins and allowed precise estimates of crustal thickness across the Moon. This directly supports the idea that a thicker crust on the far side prevented widespread volcanic activity. Gravity mapping, especially by Lunar Prospector and Grail, added another crucial piece of the puzzle. Grail's high-resolution map showed the so-called mascons, or mass concentrations, linked to the dense basaltic lava of nearside Maria. The far side lacks such prominent mascons, reinforcing the scarcity of large lava deposits there. Gravity data also provided indirect evidence of varying crustal thickness and uneven mass distribution within the Moon, both key factors influencing where volcanoes could form. Finally, compositional mapping confirmed the differences in rock types. Instruments like Lunar Prospector's gamma-ray spectrometer, Clementine's multispectral imager, and LRO's Diviner Lunar Radiometer identified the basaltic composition of Maria and the anorthositic composition of the highlands. Crucially, Lunar Prospector's measurements of radioactive elements provided direct evidence for the near side's concentration of internal heat, supporting the theory that uneven heating drove the Moon's volcanic asymmetry. Diviner further mapped thermal emissions, distinguishing between different mineral types and confirming the varying distribution of volcanic rocks across the lunar surface. The far side scarcity of Maria is not the result of a single factor, but a combination of events and conditions: uneven internal heating, differences in crustal thickness, the presence or absence of massive lava-filled basins, and possibly even early patterns of mantle flow. Together, these elements paint a picture of a Moon whose interior and volcanic history were remarkably lopsided, with the near side flourishing with volcanic plains, while the far side remained largely silent and barren. The unusual difference in volcanic activity between the near side and far side of the Moon has deep and far-reaching consequences for understanding lunar geology and its long-term evolution. This striking volcanic imbalance is one of the clearest signs that the Moon did not evolve evenly. It shows that internal processes, shaped by uneven heat inside the Moon and differences in crustal thickness, work together with external impacts such as meteorite collisions to create two very different hemispheres. Studying this asymmetry offers vital clues about the Moon's thermal past, revealing that the Moon cooled at different rates in different regions and that its internal heat was not spread evenly. It also enriches our understanding of how the lunar crust was built and changed over time, confirming that the Moon's early crust, formed from a global ocean of molten rock, developed uneven thicknesses. These variations had long-lasting effects, shaping where volcanic activity could occur and where it could not. By examining this unusual volcanic pattern, scientists can also draw important comparisons with other planets and moons. It helps explain why some planetary bodies show widespread volcanic activity while others remain largely unchanged, depending on factors such as their size, internal heat, and the properties of their crusts. For future lunar exploration, the scarcity of large lava plains, or maria, on the Moon's far side means that this hemisphere offers very different geological targets. Explorers will find mostly ancient highland terrain, shaped by early processes rather than massive volcanic flows. The far side of the Moon, therefore, serves as a relatively untouched record of the Moon's earliest history, preserved precisely because it was largely spared from the enormous lava floods that transformed the near side. This dramatic imbalance in volcanic activity continues to be one of the most intriguing and important chapters in the story of our Moon, offering a window into the hidden workings of our nearest celestial neighbour. The surface of the Moon is an incredibly harsh and unforgiving environment for any kind of life. One of the main reasons for this hostility is the constant and intense bombardment of space radiation. Unlike our home planet, Earth, which is protected by a strong magnetic field and a thick life-supporting atmosphere, the Moon has neither of these vital shields. As a result, its entire surface is directly exposed to the full range of cosmic and solar radiation. This exposure poses serious health risks for any future human explorers and creates significant challenges for the long-term operation of robotic or uncrewed equipment. NASA has devoted considerable effort and resources to studying this radiation environment in detail, particularly through missions like the Lunar Reconnaissance Orbiter, commonly called LRO, and through the first-hand experiences of the Apollo astronauts. Understanding these radiation levels, especially on the far side of the Moon, is absolutely essential for planning any extended human presence beyond low Earth orbit. Space radiation is mainly made up of two key components: galactic cosmic rays, abbreviated as GCRs, and solar particle events, or SPEs. Galactic cosmic rays are incredibly high-energy particles that come from outside our solar system. They are often created by violent events in distant galaxies, such as exploding stars known as supernovae. These particles are mostly atomic nuclei stripped of their electrons, including protons, helium nuclei, and even heavier ions. Travelling at nearly the speed of light, GCRs are ever present, forming a continuous background of radiation that fills the entire solar system. Because of their extremely high energy and tiny size, GCRs can penetrate almost anything. They can pass through spacecraft walls and even through relatively thick shielding, making them very difficult to block. Long-term exposure to GCRs is a serious concern for astronaut health during missions that last months or even years. Solar particle events, in contrast, are sudden and sporadic bursts of high-energy particles ejected from the Sun. These events are often linked to powerful solar flares and coronal mass ejections, massive eruptions of plasma and magnetic fields from the Sun's outer layer called the corona. SPs are mostly made of high-energy protons, but they can also contain electrons and heavier ions. Unlike the constant presence of GCRs, SPs are unpredictable and can vary greatly in intensity. When a strong SPE occurs, it can deliver dangerous, even lethal doses of radiation in a very short time. Their occurrence is tied to the Sun's roughly 11-year cycle of activity. During periods of high solar activity called solar maximum, SPEs become more frequent and more intense. While the exposure from an SPE is brief compared to the chronic background of GCRs, it poses an immediate and serious threat to anyone on the lunar surface or in space. Earth, in stark contrast, enjoys powerful natural defences against these particles. Our planet's global magnetic field, also called the magnetosphere, deflects most charged particles from both GCRs and SPEs, bending them around the planet. The few particles that do manage to get through are mostly absorbed by Earth's thick atmosphere, which acts as a sturdy physical shield. This combination of magnetic and atmospheric protection makes Earth's surface and even low Earth orbit relatively safe from the most damaging forms of space radiation. For example, the International Space Station, which orbits well within Earth's magnetosphere, benefits from this shielding and experiences radiation levels far lower than those in deep space or on the Moon. The Moon, however, has no substantial atmosphere and no global magnetic field. Its entire surface is completely exposed to both GCRs and SPEs, with nothing to block, absorb, or deflect these dangerous particles. NASA first began gathering direct data on lunar radiation during the Apollo missions of the 1960s and 1970s. Astronauts carried personal dosimeters, small devices designed to record the total amount of radiation they were exposed to. These measurements revealed that radiation levels on the Moon, both on its surface and in lunar orbit, were far higher than anything experienced in Earth orbit, confirming the lack of natural protection. Specific experiments such as the Apollo Passive Dosimeter Experiment, called APDE, and cosmic ray telescopes were also carried on some missions to better understand the radiation environment. These early data were critical in highlighting the need for strong protective shielding for future human missions. While the Apollo astronauts only spent a few days on the lunar surface, limiting their total exposure to GCRs, they still had to be prepared for sudden solar particle events. Training included retreating to the more heavily shielded command module in the event of a severe solar storm. The most thorough and continuous measurements of lunar radiation have come from NASA's Lunar Reconnaissance Orbiter, or LRO, launched in 2009. LRO carries a specialized instrument called the Cosmic Ray Telescope for the Effects of Radiation, or CRATER. CRATER's primary mission is to measure radiation on and around the Moon with great precision and to study how different shielding materials reduce its effects. The instrument uses detectors made from tissue-equivalent plastic, which imitates human tissue, allowing scientists to directly estimate the radiation doses astronauts would receive. Orbiting the Moon, LRO provides global coverage, meaning CRATER systematically measures radiation across both the near and far sides. The data consistently confirm that GCR levels are extremely high everywhere on the Moon. Measurements indicate that radiation dose rates on the lunar surface are roughly 2 to 3 times higher than those experienced on the International Space Station, underscoring the far harsher environment beyond Earth's protective bubble. While the Moon itself offers some shielding from particles coming from below, most radiation exposure comes from particles arriving from above or from the sides, making lunar surface activity particularly risky without substantial protection. In recent years, scientists have finally been able to obtain direct measurements of radiation on the far side of the Moon, thanks to China's Chang'e 4 mission. This groundbreaking mission successfully landed its rover, Yutu-2, within the enormous South Pole Aitken Basin, located on the Moon's far side in January of 2019. The lander carried instruments specifically designed to study radiation, including a lunar neutron detector and a dedicated radiation sensor. The data gathered by these devices provided the very first long-term, direct readings of radiation from the lunar far side. These measurements largely confirmed what had been inferred from orbit by NASA's Lunar Reconnaissance Orbiter, using its CRATER instrument, and they were comparable to the radiation levels recorded by astronauts during the Apollo missions on the near side of the Moon. Together, these observations reinforce the understanding that the Moon's radiation environment is broadly uniform across both hemispheres, primarily because the Moon lacks a global magnetic field and a thick atmosphere to shield its surface. Understanding the nature of lunar radiation on both the near and far sides is critical for planning human missions. Galactic cosmic rays, or GCRs, create a constant, low-level but highly penetrating background of radiation. While this type of radiation is not immediately deadly over the course of a typical mission, long-term exposure poses serious health risks. These energetic particles can damage DNA, cells, and tissues in cumulative ways that may manifest years later. Because of their extremely high energy, GCRs are very difficult to block completely, requiring thick layers of shielding to reduce their impact. Solar particle events, or SPEs, present an even more acute threat. These events occur unpredictably and can release a sudden flood of energetic particles, which could deliver a potentially lethal dose of radiation to unshielded astronauts in just a few hours. This makes robust warning systems and rapid protective measures essential. When primary radiation from either GCRs or SPEs strikes the lunar surface or the walls of a spacecraft, it can produce secondary radiation, a process sometimes called splashdown radiation. This secondary radiation includes neutrons, protons, and heavy ions, and it adds to the total radiation dose astronauts receive, making careful habitat design all the more important. The health risks posed by lunar radiation are serious. Short-term effects, though unlikely for brief missions unless a major SPE occurs, can include acute radiation sickness, producing symptoms like nausea, vomiting or severe burns, and potentially incapacitating astronauts. The more subtle, long-term effects, particularly from ongoing exposure to GCRs, are even more concerning. These include an elevated lifetime risk of cancers, damage to the central nervous system that could impair cognition and lead to neurological disorders, cardiovascular disease, and cataracts. GCRs are particularly dangerous because they consist of highly energetic heavy ions, which create complex tracks of damage in biological tissue that are more difficult for the body's natural repair mechanisms to fix compared with other types of radiation. Given these hazards, planning any long-term human presence on the Moon, especially on the far side, requires detailed strategies to protect astronauts from radiation. One of the most effective and readily available shields is the lunar regolith, or surface soil. Thick layers of regolith can absorb and deflect radiation, making it a valuable natural resource for habitat protection. Future lunar bases may be built either under thick layers of bulldozed regolith, or within existing lava tubes, or even underground structures specifically designed to take advantage of natural shielding. A regolith layer several meters thick could dramatically reduce exposure to both GCRs and SPEs, offering essential protection for astronauts living on the Moon. In addition to physical shielding, early warning systems are vital. Continuous monitoring of solar activity from Earth-based observatories and dedicated satellites can alert crews to incoming solar particle events, giving them valuable hours, or even minutes, to reach heavily shielded storm shelters within their habitats. These shelters would be fortified with dense materials such as water, polyethylene, or thick layers of regolith to absorb the incoming radiation. Mission plans would need clear protocols for rapid crew movement to these shelters during high-risk periods. Other protective strategies include limiting the duration of emissions to reduce total radiation exposure, particularly during periods of heightened solar activity, and selecting crew members based on individual susceptibility to radiation, although this area is still being actively researched. Scientists are also exploring pharmaceutical solutions, such as drugs that could repair radiation-induced cellular damage or enhance DNA repair, though these treatments remain largely experimental. Although the Moon's lack of a magnetic field and atmosphere makes radiation levels generally similar across its surface, small differences exist. For example, Earth's magnetotail, a long extension of our planet's magnetic field, occasionally sweeps across the near side of the Moon, providing a very slight and temporary reduction in solar particle flux. The far side, by contrast, lies almost entirely outside this minor shielding effect, experiencing a more consistent and direct exposure to cosmic rays and solar wind. This distinction is minor in the overall context, but it underscores just how relentless the far side's environment can be. More importantly, if a major SPE occurs while astronauts are on the far side and simultaneously behind the Moon, where direct communication with Earth is blocked, receiving real-time alerts becomes impossible. This highlights the need for autonomous, on-site radiation monitoring and emergency protocols that can be executed without immediate guidance from mission control on Earth. Thanks to decades of data from the Apollo missions and instruments like NASA's Lunar Reconnaissance Orbiter, we now have a detailed picture of the Moon's radiation environment. Still, this challenging aspect of lunar exploration demands creative engineering solutions, careful operational planning, and rigorous safety protocols to ensure the health and longevity of any future human presence, whether on the near side or the far side of the Moon. Studying the insides of celestial bodies through their vibrations, a science called seismology, gives us a unique glimpse into their hidden interiors. Just as earthquakes on Earth send waves rippling through our planet, helping scientists map its crust, mantle, and core, the Moon experiences its own subtle tremors, called moonquakes. These moonquakes create waves that travel through the Moon, revealing the layers concealed beneath its surface. Although the Apollo astronauts only set up seismic instruments on the near side of the Moon, the long reach of seismic waves allowed NASA scientists to infer the structure of the far side indirectly, giving humanity its first profound understanding of the Moon's hidden half. This network of instruments was not just a technical feat, it was a pioneering effort that opened an unprecedented window into the Moon's deep interior. The Apollo Lunar Seismic Network was a monumental scientific project. It began with Apollo 11 in July of 1969, when astronauts placed the first seismometer on the Moon. This early device was relatively simple and only operated for a short time. The project became far more ambitious with Apollo 12, which landed in November of 1969, followed by Apollo 14, 15 and 16. Each of these missions installed advanced passive seismic experiment packages, highly sensitive instruments designed to listen continuously for even the faintest vibrations on the lunar surface. The placement of these instruments was carefully planned. All 4 long-lasting stations were positioned on the Moon's near side, relatively close to the equator, forming a triangle that allowed scientists to pinpoint the locations of quakes. This near-side focus was not arbitrary. It was dictated by the practical realities of human exploration, including the need for constant communication with Earth and the limitations of mission objectives that focused on near-side landings. Despite this limitation, the Apollo seismic stations provided a treasure trove of data over many years. The instruments deployed during Apollo 12, 14, 15, and 16 operated continuously until September of 1977, when they were finally switched off due to budget constraints. This extraordinary operational period, spanning more than 8 years, allowed scientists to record thousands of moonquakes and meteoroid impacts, far surpassing what any brief mission could achieve. The seismometers were powered by radioisotope thermoelectric generators, RTGs, which converted heat from radioactive decay into electricity, allowing them to function even during the long, cold lunar nights. All collected data was transmitted back to Earth, where NASA scientists meticulously analysed every faint signal. Through these observations, scientists identified several distinct types of moonquakes. The most common were deep moonquakes, which originate hundreds of kilometers below the surface, typically at depths of about 700 to 1,200 kilometers, roughly 430 to 750 miles, within the Moon's mantle. Remarkably, these deep moonquakes are strongly linked to the Moon's relationship with Earth. They tend to occur when the Moon is at its closest or farthest point from Earth in its slightly oval orbit, or when it aligns with the Sun, moments when tidal forces stretch and squeeze its interior. In essence, Earth's gravity tugs at the Moon, triggering these tremors. Although deep moonquakes are small compared to earthquakes, they last an unusually long time, sometimes tens of minutes, even over an hour. This prolonged reverberation happens because the Moon's crust and regolith are highly fractured and scattered, causing seismic waves to echo endlessly instead of fading quickly as they do on Earth. Analysis revealed hundreds of clusters of these deep moonquakes, many located beneath the far side of the Moon. Their waves travelled across the lunar interior, reaching the near-side network and providing indirect yet vital information about the hidden hemisphere. Another type, shallow moonquakes, is much rarer but often stronger, though still generally less intense than the largest earthquakes on Earth. These quakes originate in the Moon's crust, usually at depths of less than 200 kilometers, or roughly 120 miles. The exact cause is still debated, but scientists believe they result from stresses caused by the Moon slowly cooling and contracting, or from minor adjustments along fault lines. Unlike deep moonquakes, shallow quakes show little connection to tidal forces. Some of these events also occurred on the far side, sending their waves across the Moon's interior before reaching the Apollo stations. In addition to naturally occurring quakes, the Apollo seismic network regularly recorded the impacts of meteoroids. These range from small, random events to larger, carefully planned crashes. NASA intentionally smashed spent upper stages of Apollo rockets and lunar module ascent stages onto the Moon at known times and locations. These controlled impacts acted like precise seismic hammers, sending waves through the Moon that scientists could study to probe its interior, much like sonar maps the ocean floor. In combination, these natural and controlled seismic signals allowed scientists to construct the most detailed picture of the Moon's inner structure ever achieved. Even with instruments confined to one side, the Apollo seismic network revealed the Moon as a dynamic, living body, its interior layers and far-side mysteries gradually unfolding through the gentle rumble of moonquakes. The remarkable ability of the seismic network installed on the near side of the Moon to listen to and interpret tremors originating from the far side was a stunning demonstration of the power of seismology. When a moonquake shook the far side, it sent out vibrations in the form of seismic waves. These waves came in two main types: P waves, also called primary waves, which are compressional waves capable of moving quickly through both solid and liquid material, and S waves, or secondary waves, which are shear waves that can travel only through solid matter. As these waves travelled through the Moon's interior, they eventually reached the Apollo seismometers stationed on the near side. By carefully measuring how long it took for the P waves and S waves to arrive at the various stations, scientists could pinpoint both the location and the depth of the moonquake, much like triangulating the epicenter of an earthquake on Earth. Even more importantly, the way these seismic waves moved through the Moon revealed critical clues about the density and rigidity of the materials they passed through. Whenever the waves encountered a boundary between layers or a change in the state of material, such as a transition from solid rock to molten matter, their speed and direction would shift, and some waves could even be reflected or absorbed. One of the most exciting breakthroughs was the discovery of shadow zones. These are regions on the opposite side of a seismic event where certain waves fail to arrive. For example, if S waves from a far-side moonquake did not reach particular near-side seismometers, it indicated that the waves had passed through a region that was not fully solid. This strongly suggested the presence of a partially molten or liquid core. Indeed, careful study of S waves from deep moonquakes, as well as from deliberately planned impacts on the far side or through the Moon's centre, provided convincing evidence for a small, partially molten core at the heart of the Moon. The fact that S waves passing near or through the very centre were missing or severely weakened was a clear sign that this core was not entirely solid. This discovery was profound, overturning earlier ideas that the Moon's interior was completely cold and inert. Analysis of the seismic data allowed scientists to estimate that this core is relatively small, making up roughly 20% of the Moon's total radius. While modest in size, its partial molten state demonstrated that the Moon still holds some internal heat and is not completely geologically dead. Seismic waves from far-side moonquakes and impacts also offered a window into the structure of the Moon's mantle and crust. By observing the travel times and properties of P waves and S waves, scientists could detect variations in density and rigidity within the mantle. Although the lunar mantle is more rigid than Earth's, reflecting its faster cooling over billions of years, it is still capable of generating deep moonquakes under tidal stresses. The patterns of scattering and weakening of seismic waves revealed that the upper crust is highly fractured, a testament to billions of years of meteorite impacts and impact gardening. Even though no seismometers were placed on the far side, the way waves travelled through its crust and mantle provided indirect yet valuable information. Differences in wave behaviour compared to near-side events offered further clues about the overall structure and degree of fracturing beneath both hemispheres. The broader implications of these seismic discoveries for understanding the Moon's interior and evolution are profound. First, the Apollo seismic network conclusively confirmed that the Moon has a layered interior, a crust, a mantle, and a small, partially molten core. This layered structure is essential to understanding how the Moon separated from its original molten state. Second, the identification of a partially molten core reshaped existing models of lunar thermal evolution, revealing that the Moon retained more internal heat for longer than previously believed. This lingering heat would have fueled ancient volcanic activity and, as magnetic evidence suggests, may have driven a brief lunar dynamo in the distant past. Third, the nature of moonquakes themselves, mostly caused by tidal forces or shallow fracturing, demonstrated that the Moon lacks active plate tectonics like those on Earth. The absence of large, powerful quakes and the unique characteristics of moonquakes reinforced the view of the Moon as a largely geologically quiet body, where major crustal movements ceased billions of years ago. Fourth, seismic observations offered vital constraints on the Moon's internal temperature profile. A partially molten core implies a specific temperature range, helping scientists refine models of how the Moon cooled over cosmic time. Finally, though the seismometers were all located on the near side, the waves from far-side events carried valuable information about the Moon's asymmetry. By travelling through and interacting with the far side's distinct crust and mantle, they helped build a more complete picture of the Moon's interior when combined with gravity and compositional data. The Apollo seismometers continued operating for decades after the astronauts departed, tirelessly listening to the Moon's faint internal tremors. This long-term data provided an invaluable legacy, revealing hidden secrets about the Moon's interior, its thermal history, and its long-forgotten geologic activity. Insights that continue to guide our understanding of our celestial neighbour even today.